Inch wait, as always. I think today I'm gonna start with studying the source code, and then after that I'm gonna read the book again, the chapters. Read all of the other articles that I had here yesterday. So I'm gonna read the chapters again for the book, this issue about cryptography and wallets, and read the yellow paper. Or maybe read the Casper algorithm, which is the proof of stake. But I'm debating on whether or not spending too much time on this or moving on to another chain, because after reading a bunch of stuff, I don't believe in Ethereum, I think, long term. Especially after I read the last document that I was reading now, which is about the attack vectors on Ethereum. And it says that for 33% or 50 and 70%, something like that, for this percentage attacks, which means that when someone has 30% or 50% or 70% of the network, the last layer of defense is the social layer, which means that it's pretty much relying on coordination for the chain to be resilient. And I really don't buy that. I think that's not going to work on the long term. So if it stays like this, I don't think it is. I think ultimately it's going to fail. It might last for a long time, but I think eventually it's going to fail. So I think I need to study for other alternatives, but at the same time, I want to understand more how it works, because, like I said before, everything's connected. So by studying one of them, like by studying Ethereum really in depth, it's gonna be easier to understand the other protocols, because it's probably gonna be variations of the same things. So the part that I wanna really understand is how does it work with the uncle blocks and the mempool, like the flow of information. That's the most important. And then the cryptography part, which is very difficult, and I'm gonna leave it for later. I also thought about some stuff today, which I think it makes a lot of sense, and it really opened my mind. And I think it seems very obvious. Maybe it is obvious for other people, but for me, it's like really eye-opening, let's say, or crazy to think about. And I think I'm gonna explain this shortly. First, let me give this repository. Outline an explanation of each folder in the file. Or folder. Hopefully I can still use now. It's not a peak hour. I think I might get ChatGPT, but not right now, maybe in the future. So what I was thinking about, let's see if I can do Skelly draw. Is that, and I made a tweet about this. I have the X and Y coordinates in the Cartesian plane. And I was thinking about, like, if you have a bunch of data, the connection of the data is going to be the functions. So if you imagine all the points possible in the Cartesian plane, then you don't have any meaning because you don't have a function. So a function is the relationship between past and future, and it is the connection between the data points in the Cartesian plane. So if you have a bunch of points here, like if you have enough points that it just fills up the whole plane, then you don't have any pattern of movement because you have all the possibilities in the plane. But if you have the connection of specific points, then you have a function. And then what I realized that is that because of this, everything in mathematics is an equation, which represents the function, which represents the connection of the points. And this connection has the embedded assumption of a symmetry, because that's what equality is. So functions are the extension of symmetries that connect different points. So the connection of different points in data that call function are different reference frames that have embedded assumptions into them, which are the symmetrical properties. And the Cartesian plane itself is a projection of perception. So that's why the way that we observe things and we make conclusions about them is by putting different relationships on the Cartesian plane. But if you think more about it as well, is that if you have 3 coordinates, then you're gonna have space. So if you put more coordinates, then you have a different representation of the data because you're putting more perception into it. So you can either go up to 4 to 3, which is space, or you can change the relationship between things here and you get different properties. So what I realized is that mathematics itself is a projection of perception, and that it's an extension of an extension of an identity that creates mathematics. So mathematics is the geometrical object of the representation of perceptions from an identity frame, because everything is always relativistic to that identity frame that creates the relative symmetries. And I'm not really sure if that's like obvious for other people, but what that implies is that everything you do and you calculate in mathematics is already a consequence of your identity, because you are representing things with abstraction that is the connection of the geometry of space-time, because you are embedded in space-time. So all the connections of data points that you have that make up the geometry are going to be the functions that you represent, and those functions have the embedded assumption of the symmetry that you create when you parse the information of space-time into a relative reference frame of your identity. So that means that it's kind of like a hologram, and you lose resolution because what you're representing with the mathematical objects is an extension of your perception. So geometry itself is a lower level resolution of your projection. And that's what mathematics is the connection of space-time. And in that, you have the multifactorial structure of identity, which is these connections of reference frames, that of the connection of these relativistic symmetries with each other that create the nature of geometry and create functions. So you reach harmony by connecting different functions together. And that's where you have a space of conscious agents, I think, that create space-time, because the thing that you're perceiving is the harmony of the connection of different perspectives, I think. So that's one of the reasons why I think that but the question that arises from that is that how can you measure something that you don't perceive? That's the challenge here. It's like, because how can you discover a mathematics if you can't perceive outside of what you project? That's the question. So what that implies is that mathematics is never going to be strong enough to understand the higher level reality that encapsulates space-time, because it's already a projection of an identity that has all these embedded assumptions of symmetries, because it is what it is. It is the geometry. So how do you go from outside of that? Then it becomes the challenge, because it's the whole paradox of the quantum mechanics, where the observer is always entangled with what is observed, because it is what it is. Like the whole thing is the object, and that's what happens in mathematics here. But I think that at the horizon of mathematics is the complex plane. That's why I think that the answer to understanding higher dimensions of reality is on the complex plane. And that's probably related to, I haven't studied the mathematics of quantum mechanics yet, but I think that quantum mechanics is very related with the complex plane and also black holes, because it seems to me that the complex plane is the mathematics of the imagination, and imagination is the connection of space-time. So the grading of the identity that creates the space-time is the distribution to the highest level density, which is what we call space-time, and imagination, which is perceived to be outside of space-time, but is the same thing because it's a gradient of distribution of densities. And I think that as you approach the S-curve, the asymptote of space-time, you get into imagination, and the boundary between the two is probably at the complex plane. So the multifractals at the complex plane allow, if that is true, then it will allow to increase the probability of predicting the future, because the connection of the flow of information in relationship to a reference frame of an identity is done through the flow of information goes from the complex plane to space-time, I think. Obviously, I'm not really sure, like, if any of this makes sense, but it is really obvious, like, now that I think about it, but I never really looked at things this way, I think. And I think it makes a lot of sense. So every time that you're calculating something with using Cartesian coordinates, and you are making functions, you are projecting your perception into the plane. And then the relationships that you're seeing is like a representation of the data structures that you experience, which is space-time. So it's an extension of geometry. And I think obviously machine learning is going to be related to that, because what machine learning is all about is reducing the data into functions. Like, that's the whole point. So it's always relativistic. That's the thing. But yeah, it doesn't have too much to do with what I'm gonna do now, but I thought that I had to just say that this stuff. So what I'm gonna have in my mind is how can I find the boundary of perception? Like, how can you discover different realities? Because it seems like an impossible problem. Because you're always limited by your perceptions. So any tool that you're gonna use, the mathematics and language, is gonna be a projection of that, which is a hologram, which is a lower level resolution of the higher reality. I think that is also related to, obviously, to the P equals NP problem. It has to be related because all of the polynomials is like a function. So the irreversibility of polynomials has to do with the identity structure that creates the relativistic symmetry that creates the function. So it's all about perspective, I think. But the boundaries are, it might be the case that the boundaries of computation that make up the structure of space-time are irreversible because it loses meaning if it becomes reversible. Because then, like, how do you define what is real from what is fake? These two things are codependent. You can only define something as being real if it's useful in the current reference frame that you're existing at, which is related to survival. So it might be the case that P equals NP, but the problem is that it only equals NP into the imagination realm after the boundary that makes up space-time. That means that even if that's true, then it doesn't matter because the laws are not applicable to space-time. So it doesn't interfere with survival, I think. It is still very interesting to think about. Actually, I'll put this one here. Assume that this is program counter of the instruction. I don't think I'm gonna spend too much time on this one because it's more related to how the OP codes, I think, were programmed. For the stack manipulation and memory manipulation on the EVM. The whole thing about mathematics, I'm still thinking about this. Like, the biggest problem with the stuff that I talked about is that it still doesn't say anything about the nature of perception, like how is perception created, and how the distinction is created, because it can't come from anywhere, because that's already implying the notion of space-time. And it seems like an impossible problem because it seems like you're trapped into a box that, but it has to be, there must be a way to understand it. But the problem is, I think that it might be the whole thing about enlightenment, that you can understand it, but you can't understand it from the paradigm of knowledge or abstraction, because abstraction is already embedded inside of the paradigm that you are creating. Because the whole thing about distinctions in mathematics is that it is the consequence of the perception. So you can't use that to understand the nature of perception itself. If that's true, then it's a problem, because then, like, there isn't the framework to go beyond that is unclear, I think. You can do it through awareness, like people say, like meditating, but what does that even mean? Like, it's hard to, because then it can always be the case that you're delusional about enlightenment. That's the thing. It might be true for you, like, and I get that you is the only thing that exists because you can't separate yourself from other, because it is the same thing. You create a distinction. That's what the identity is, and that's what the perception is, but it becomes kind of meaningless, because then it's like everything goes and nothing goes at the same time. So that's why it's very paradoxical, I think. It's probably, I think this has to do with the tree, syntax tree, because of these lexers, the word here, lexer. So the parsing of the language, like this is what creates the language, I think. The low-level assembly, I think, is U or something like that, the name, for the OP codes that determine the instructions in the EVM. Let me go on the other ones. I think the ones that are going to be interesting is the transaction pool and the state. Probably. Maybe the raw database. I should copy this first and then the other one. Yeah, makes sense. It's kind of difficult to understand though, the code, because it's mainly done with these letters here. But it's the array of bytes, then it does the cache 256 of the bytes. Crypto is probably another package somewhere. Yeah, here. I remember looking at this thing here. It also has the elliptic curve thing. I think this is the folder where they keep all the cryptography related to the project. Makes a lot of sense. And it gets the indexes and makes it equal to the bytes, changes the bytes. No, equal to the elements in the bytes here. Bytes array. Partial match is pretty self-explanatory, I think. It's not that interesting because it's not related to what I'm trying to, but it's actually not that hard actually to understand, I think. It seems hard on the beginning, but I think it's not that difficult. It's harder to write this stuff, I think, than it is to read here and understand. I don't understand what this make function is. It's probably some Go function. Yeah, there's a built-in function from Go. So it's kind of like a default dict or some function like that in Python. It's a function used to create a certain data structure. And chan is probably channel, short for channel. I think that this is related to threads, so I don't really know how it works really well, because I never studied Go, but I think you can open multiple different threads to have a concurrent code running, which gets more complicated because then you have the thing about race conditions, which is when two different threads try to access the same memory space. And ask what this is. I assume it is channel. A chan here. Channels, yeah, makes sense. Blah blah blah. I don't think I'm gonna spend too much time on this one. I'm gonna go for the ones that I'm more interested about first. I think I might not even study this into much depth because of the stuff that I said, that I don't really believe anymore that Ethereum is gonna be the chain that is the biggest, let's say. Maybe it will have a purpose, but I don't think that is gonna be. I think it's the MySpace version of Web3. I think there's gonna be something else that it is like the Facebook or something else. And I think that it's all about the consensus protocol, like the game theory of the consensus and the flow of information as well. One thing that I still don't understand is if it is necessary to create blocks to have the blockchain, because the whole logic is that you create a block and then you use the nonce of the block and the other parameters that each block has to create the hash functions that connect the blocks, and that's the structure. And now it's getting more complicated because it's going from Patricia tree to the other tree structure. But the thing that maybe this is always the case because that's the only way to make it more efficient, but the thing that I don't understand is if it is possible to create one that there isn't a block. It's just connections of transactions, because that way you would eliminate the whole ordering of transactions inside of the block if you had but then what makes me think that this is not the problem, because I think it's a fundamental problem, because it's gonna go into one of those things that is just a fractal pattern, because it doesn't matter how many times you break down, it's like a fundamental problem with the logic of the data structure. So you can go either way, saying like let's reduce to the least amount of space possible, which is one transaction, or let's go to only one block, which would be the two extremes of the gradient. And I think in both scenarios you would still have the problem of the order of transactions. The only thing that would change is the nuance of the game theory, the complexity of the game theory that revolves around the transaction ordering. And I think that this is the case because it's probably related to something more fundamental, which is the physics of transactions itself and how they evolve over a network. Synchronization between, so it's similar to a Node.js with data streams, I think, where you have different commands that you can do to like create different pipes of information that organize the different threads. I think Node is single-threaded, but like I think the concept of the flow, the data stream, is the same, I think. The only difference is that Go is gonna be you can have multiple threads, and Node.js you only use one thread. So the only difference is on the structure of the pipes, I think. It looks like it's taking a long time, so I'm just gonna let me see if here there's anything that seems interesting. This one obviously blocks also sounds interesting. EVM. Let's look at this show first. I need to study more the data structure as well to understand. I read all of the articles, but I didn't stay a long time trying to understand the code itself of the data structures. Yeah, this is the problem that I'm talking about. That each thing is gonna be from a different library, and then it's hard to know, because then I have to open a bunch of different tabs to search for each thing. That's why I wanted to create the script visualization thing, but and I keep thinking about building that again, but the problem is that I think it's too difficult. It's like not difficult in the sense that I can't do it, but difficult in the sense that it takes too much time. Because then I'm gonna have to explore how to get all the under the hood stuff, the stack trace, the imports system. Like maybe I can create something that parses the file, and then based on the syntax I can create a syntax tree. Like create a dictionary, then you put the names here, and then you put the logic that it wants to happen once it encounters the names on the files, and then you create the tree structure that way to connect everything. But I think it just takes too much time, but I'm not really sure. Like I'm still trying to think in my mind if it's something that makes sense to do or not, or to invest time on, because it would help a lot, I think, to visualize how everything is connected. Because then here I would be able to visually see like where this function is pointing to and where that other function is connected, the whole application. And here is just the type. So not sure if it comes from this file. This is the mining algorithm, I remember that. Consensus.go. I think I'm gonna spend more time studying the proof of stake one, just because it's the one that is being used now. So I think that it makes more sense if I'm going to build something later, even if I don't build on Ethereum, because I know that there are also other protocols that use proof of stake and variations of that. And also I think that proof of work is also not going to be used very much in the future because it takes too much energy. Obviously I want to understand that as well, but I don't think I have time to study everything. So as far as I understand now, the difference between proof of stake and proof of work is that on proof of stake you have blocks of time. So at each, which are called epochs, I think, which comes from machine learning. They use machine learning, they use epochs in machine learning as well. So each epoch is like one iteration, and this happens on a time frame. And then for each epoch, some validators are selected randomly to validate the block. And then you have the block builder, which is separated from the validator. So you have two different APIs, which is two different peer-to-peer networks, which are connected to the execution client and consensus client. The execution client creates the block, I think, and the consensus client is the one that validates. The consensus is like the lighthouse client that I'm running here, and the execution is the GIF client. So I think that's another thing. This whole thing here is related to the execution client. I have to remember that. So this whole code that I'm studying now is related to the execution part, which I think is related to the block building part. And then the other one is the consensus part, which is the validation of the blocks. So the way that it works, the builders build the block and then they propose the block to the validators. And then at each epoch, there is the selection of one of the validators to validate the block. Something like this. And then if you use flashbots, then you have 3 different clients. I don't remember really well what's the third client though. Is it execution? I don't remember really well. It might be just the MEV boost, but I forgot the name of the client. Let's see. Boots. Validator, client, consensus, and execution. And so the one that I forgot is the consensus. So here he's saying that any POS needs to run those 3. Maybe we need to read the documentation again. I think I'm gonna do that. I'm not gonna read the attack vectors thing because I remember it's the longest one, but I think I'm gonna read it again, the documentation on proof of stake to understand more. I forgot as well when I was studying this that this part is only related to the execution client. It makes a lot more sense, and what I'm probably gonna do after I study this is study the lighthouse as well. And there are multiple different implementations also. But I think that the only thing that changes between them is the language. Obviously, like, you can't change the fundamental consensus because that way the blockchain wouldn't work. It would be like, depending on which client you're running, you are running a different blockchain. I don't think that's the case. I think it's just using different languages to communicate with the same protocols. So the way that you're gonna capture the data is different because you're using a different language, but use the same data and you're using the same data structures and using the same consensus mechanism. I think I'm gonna close this one and go back to reading this. And this is the EVM. I know that there is a difference in the information that you have on each block on proof of stake as well. Because I remember from the documentation, but I forgot, or I didn't remember really well what parts of the documentation what parts of each block are important for the consensus. Let me read this again. It's a sidecar for Beacon Node, a separate piece of open source software which cures and outsources block building through a network of builders. That's the other thing that I think I just confirmed yesterday as well, is that if you are a node, you have the option to validate transactions off the chain. You don't need to pass the transactions to other mempools. Like, you can validate all of them yourself and then only pass after validating. But I think what you can't do is... That's the thing that is confusing, because there's also the thing about reorg attack, where you can't change the order of blocks, obviously, because that would change the whole MEV thing. So it is considered as an attack, but I guess in proof of stake is different than proof of work. That's why I'm confusing the two. Because it does make sense that... Because I think on proof of stake, every node needs to validate each block. But I might be wrong about this. And the difference is that when you have proof of work, the miners are mining different blocks. So it might be the case where you have different histories at the same time, because different nodes are receiving different transactions. And then they're propagating those transactions through the network at different rates. And that's... Naturally, it seems logical that this would lead to different orders of blocks on each node, unless they all have to stop validating at some point, or like change their local history at some point, depending on the history of other nodes, which I think it is what happens. But how that happens is the thing that doesn't make sense to me. And I think proof of stake is slightly different because the mechanism of the synchronization is different. So this is what I have to understand this as well. Maybe I should ask ChatGPT. I always don't know how to write this thing here. The problem is that it's gonna give me a general answer, because I would have to place all the nuances of the Ethereum proof of stake version. Maybe I should read the paper. I downloaded the paper of Casper, which is the consensus algorithm I think that they are using. Blaze aggregate blocks from multiple builders in order to select the block with the highest fees. One instance of MEV boost can be configured by a validator to connect to multiple relays. The consensus layer client of a validator proposes the most profitable block received from MEV boost through the Ethereum network for attestation and block inclusion. MEV boost security assessment was conducted on 2022. Additional audits of surrounding infrastructure such as Flashbot's relay are currently underway. Additional information to be found. Security section of repository. So you have searchers, you have private order flow, and then you have the builders that are going to build the specialized blocks based on the MEV. They're going to pass to different relayers, which are just the bridge between... They're using RPC methods to connect to their own nodes, I think. And they are using MEV boost to... that's the part that I don't understand. I guess because you have a bunch of relayers that are using RPC methods, if you use MEV boost, there's like a peer-to-peer mechanism that connects them and selects the highest block from the relayers, the most valuable block for the relayers, to pass it to the consensus client, and then the consensus validates. So this whole flow here is analogous to this one, but with extra layers of complexity to optimize the block building. And then obviously if you only use the execution client, you're fucked because you're gonna be front run. And this whole thing here seems centralizing as well. Okay, it's gonna follow the Pareto distribution. I don't see how it doesn't. Because of the whole infrastructure thing. And on top of that, you have the fact that it's proof of stake, and then the people that stake the most are gonna gain the most, which is already not a lot of people, because the amount of stake you need is very high. If not a lot of people have the money, except the institutions. But then over time is always gonna be flowing for the Pareto distribution, and then to rely on coordination to solve the risk of attacks, I think is too weak of an assumption. Because we already see that politics is not strong enough to regulate market economies in the global scale. So if you gain more power in the network, it's gonna break down, I think. It's just not strong enough. Obviously, I can be wrong about this, and these people that are building all this stuff are probably more intelligent than I am, so they might be seeing things about the game theory that I'm not. So obviously possible. I think it's weird because I think on the Ethereum documentation it says that it's only true, but I might be wrong here. Consensus. I'm pretty sure on the Ethereum documentation there's only two types of clients that they talk about, which is the execution and the validator. Because I remember looking at this to run this node here. So I'm not sure what the other one is about. It's probably here. So it's consensus and execution. I got the names wrong, but it is just two clients, I think. So maybe it's wrong here. Not sure. Yeah, execution and consensus. So I don't think there is validator. I think the validation happened on the consensus client. And the execution is the one that builds the block. So here... Yeah, the execution is the one that builds the block, and the consensus are the ones that validate. And the reason for this is because then you need less data on the consensus, which means you need less hardware. So I think the consensus use the data availability sampling technique or something like that. Maybe. I think I want to study that again, actually. Because I'm not really sure. I might be confusing the zero knowledge proof with this mechanism. I think it is the consensus though. So what they do is a mechanism where you don't need all the data to validate, and it's probably through some polynomial tricks. That way the consensus can validate that the block is correct, the transactions in the block are correct, without having to see all the transactions. I think that's what's happening. And then the block building part becomes the higher load, let's say, where it's more specialized and more centralized, because you need more hardware to have the whole chain, and also to compute the best block. Yeah, I'm definitely gonna read this one. I'm gonna read this one and this one. It's also interesting to read more about zero knowledge proofs as well. I think the next protocol that I'm gonna read is Cardano, because I know that Cardano, the people that built Cardano, were working on Ethereum, and then their proof of stake is slightly different. So I think it's a good next one to understand. So I understand the differences and the philosophical reasons or the economical reasons why people thought it would be better to build another blockchain instead of continuing with Ethereum. I'm also thinking about whether or not to finish this article here. I think I won't invest too much time on writing the articles. Like, there's a lot of information out there about this stuff already. So I think I'm just gonna write like what I'm thinking about these topics and not really concern too much about being like the best or have the most information. I'm just gonna write what I'm thinking now. I think I'm gonna finish this one today. After I read a couple of things there, I'm gonna go back and finish this. I need to find a different place to put this stuff here. And maybe I think I'm gonna create a file here. It's better. Yeah, I'm gonna grab something to eat and I'm gonna read all of this stuff. I'm gonna read the book first. Also, so I'm gonna read all of this and then read the papers as well, yellow paper and the Casper thing. I think before I read the yellow paper and the Casper, I'm going to finish writing the article there. And then I'm gonna write a small article about proposer-builder separation. I think I'm just gonna leave this one really small. But pretty much, as far as I understand now, the proposer separation thing is because of the specialization in block building and the amount of money you need because you need specialized hardware, and then because of the natural tendency of centralization in order to keep the chain decentralized and deal with the whole MEV thing, they decided to separate into two different clients, and that's the whole point of the proposer-builder separation, where before you had one client that executed the transactions and validated them, and what this leads to is the centralization, because then the clients that are able to execute become more and more centralized, so that it becomes more centralized in general, because you have to there's a requirement of the hardware to both execute and validate. But then now they separated them because then it allows more people to work as a validator, so it becomes more decentralized. That's the whole point. And then I won't dive too much into the details, I think. Just gonna finish these ones so I can post on the, so I at least have something on the blockchain portion of my blog. And then it might be a good idea to go back on these ones as well. To finish these ones about the consensus algorithms. I think actually this is a good idea. I can go into the source code and I can get the source code for yeah, but this, I think this is one is gonna take a lot more work, so it's probably better to study other, like just study a lot more before I do these articles here. Because ideally I would have two different chains with two different algorithms to show the differences, even though they both work with a proof of work or a proof of stake. But maybe I'll just do like a very simple version, because I want to study more of the other ones as well before that. Like, I think I'll do a simple version, and then after I have a decent idea of which ones I think they're the most interesting and that I want to go more in depth, then I improve the article later. the ones that I decide to go more in that. Maybe I should do the consensus algorithms first with the code. Study them first. And then go back to the whole MEV, mempool, and uncoblock thing. Problem is all related, but maybe I can superficially go over the consensus without having to look at the other stuff. That would be better, I think, because then I can finish the articles, at least the simple version. I'm gonna read this stuff. I'm gonna go grab something to eat, then I'll read this stuff here. Be right back.
Cryptography. One of Ethereum's foundational technologies is cryptography, which is a branch of mathematics used extensively in computer security. Cryptography means secret writing in Greek, but the study of cryptography encompasses more than just secret writing, which is referred to as encryption. Cryptography can, for example, also be used to prove knowledge of a secret without revealing that secret, example with a digital signature, or to prove the authenticity of data, example with digital fingerprints, also known as hashes. These types of cryptographic proofs are mathematical tools critical to the operation of the Ethereum platform, and, indeed, all blockchain systems, and are also extensively used in Ethereum applications. Note that, at the time of publication, no part of the Ethereum protocol involves encryption. That is to say, all communications with the Ethereum platform and between nodes, including transaction data, are unencrypted and can, necessarily, be read by anyone. This is so everyone can verify the correctness of state updates and consensus can be reached. In the future, advanced cryptographic tools, such as zero-knowledge proofs and homomorphic encryption, will be available that will allow for some encrypted calculations to be recorded on the blockchain while still enabling consensus. However, while provision has been made for them, they have yet to be deployed. In this chapter we will introduce some of the cryptography used in Ethereum, namely public key cryptography, PKC, which is used to control ownership of funds, in the form of private keys and addresses. Keys and addresses. As we saw earlier in the book, Ethereum has two different types of accounts, externally owned accounts, EOAs, and contracts. Ownership of Ether by EOAs is established through digital private keys, Ethereum addresses, and digital signatures. The private keys are at the heart of all user interaction with Ethereum. In fact, account addresses are derived directly from private keys. A private key uniquely determines a single Ethereum address, also known as an account. Private keys are not used directly in the Ethereum system in any way. They are never transmitted or stored on Ethereum. That is to say that private keys should remain private and never appear in messages passed to the network, nor should they be stored on-chain. Only account addresses and digital signatures are ever transmitted and stored on the Ethereum system. For more information on how to keep private keys safe and secure, see Control Responsibility and Wallets chapter. Access and control of funds is achieved with digital signatures, which are also created using the private key. Ethereum transactions require a valid digital signature to be included in the blockchain. Anyone with a copy of a private key has control of the corresponding account and any Ether it holds. Assuming a user keeps their private key safe, the digital signatures in Ethereum transactions prove the true owner of the funds, because they prove ownership of the private key. In public key cryptography-based systems, such as that used by Ethereum, keys come in pairs consisting of a private, secret, key and a public key. Think of the public key as similar to a bank account number, and the private key as similar to the secret PIN. It is the latter that provides control over the account, and the former that identifies it to others. The private keys themselves are very rarely seen by Ethereum users. For the most part, they are stored, in encrypted form, in special files and managed by Ethereum wallet software. In the payment portion of an Ethereum transaction, the intended recipient is represented by an Ethereum address, which is used in the same way as the beneficiary account details of a bank transfer. As we will see in more detail shortly, an Ethereum address for an EOA is generated from the public key portion of a key pair. However, not all Ethereum addresses represent public, private key pairs. They can also represent contracts, which, as we will see in Smart Contract chapter, are not backed by private keys. In the rest of this chapter, we will first explore basic cryptography in a bit more detail and explain the mathematics used in Ethereum. Then we will look at how keys are generated, stored, and managed. Finally, we will review the various encoding formats used to represent private keys, public keys, and addresses. Public key cryptography and cryptocurrency. Public key cryptography, also called asymmetric cryptography, is a core part of modern-day information security. The key exchange protocol, first published in the 1970s by Martin Hellman, Whitfield Diffie, and Ralph Merkle, was a monumental breakthrough that incited the first big wave of public interest in the field of cryptography. Before the 1970s, strong cryptographic knowledge was kept secret by governments. Public key cryptography uses unique keys to secure information. These keys are based on mathematical functions that have a special property. It is easy to calculate them, but hard to calculate their inverse. Based on these functions, cryptography enables the creation of digital secrets and unforgeable digital signatures, which are secured by the laws of mathematics. For example, multiplying two large prime numbers together is trivial. But given the product of two large primes, it is very difficult to find the prime factors, a problem called prime factorization. Let's say we present the number 8,018,009 and tell you it is the product of two primes. Finding those two primes is much harder for you than it was for me to multiply them to produce 8,018,009. Some of these mathematical functions can be inverted easily if you know some secret information. In the preceding example, if I tell you that one of the prime factors is 2003, you can trivially find the other one with a simple division. 8,018,009 divided by 2003 equals 4003. Such functions are often called trapdoor functions because they are very difficult to invert unless you are given a piece of secret information that can be used as a shortcut to reverse the function. A more advanced category of mathematical functions that is useful in cryptography is based on arithmetic operations on an elliptic curve. In elliptic curve arithmetic, multiplication modulo a prime is simple but division, the inverse, is practically impossible. This is called the discrete logarithm problem and there are currently no known trapdoors. Elliptic curve cryptography is used extensively in modern computer systems and is the basis of Ethereum's, and other cryptocurrencies, use of private keys and digital signatures. Take a look at the following resources if you are interested in reading more about cryptography and the mathematical functions that are used in modern cryptography. In Ethereum, we use public key cryptography, also known as asymmetric cryptography, to create the public, private key pair we have been talking about in this chapter. They are considered a pair because the public key is derived from the private key. Together, they represent an Ethereum account by providing, respectively, a publicly accessible account handle, the address, and private control over access to any Ether in the account and over any authentication the account needs when using smart contracts. The private key controls access by being the unique piece of information needed to create digital signatures, which are required to sign transactions to spend any funds in the account. Digital signatures are also used to authenticate owners or users of contracts, as we will see in smart contract chapter. In most wallet implementations, the private and public keys are stored together as a key pair for convenience. However, the public key can be trivially calculated from the private key, so storing only the private key is also possible. A digital signature can be created to sign any message. For Ethereum transactions, the details of the transaction itself are used as the message. The mathematics of cryptography in this case, elliptic curve cryptography, provides a way for the message, i.e., the transaction details, to be combined with the private key to create a code that can only be produced with knowledge of the private key. That code is called the digital signature. Note that an Ethereum transaction is basically a request to access a particular account with a particular Ethereum address. When a transaction is sent to the Ethereum network in order to move funds or interact with smart contracts, it needs to be sent with a digital signature created with the private key corresponding to the Ethereum address in question. Elliptic curve mathematics means that anyone can verify that a transaction is valid by checking that the digital signature matches the transaction details and the Ethereum address to which access is being requested. The verification doesn't involve the private key at all, that remains private. However, the verification process determines beyond doubt that the transaction could have only come from someone with the private key that corresponds to the public key behind the Ethereum address. This is the magic of public key cryptography. There is no encryption as part of the Ethereum protocol. All messages that are sent as part of the operation of the Ethereum network can, necessarily, be read by everyone. As such, private keys are only used to create digital signatures for transaction authentication. Private keys. A private key is simply A private key is simply a number, picked at random. Ownership and control of the private key is the root of user control over all funds associated with the corresponding Ethereum address, as well as access to contracts that authorize that address. The private key is used to create signatures required to spend Ether by proving ownership of funds used in a transaction. The private key must remain secret at all times, because revealing it to third parties is equivalent to giving them control over the Ether and contracts secured by that private key. The private key must also be backed up and protected from accidental loss. If it's lost, it cannot be recovered and the funds secured by it are lost forever too. The Ethereum private key is just a number. One way to pick your private keys randomly is to simply use a coin, pencil, and paper, toss a coin 256 times and you have the binary digits of a random private key you can use in an Ethereum wallet, probably see the next section. The public key and address can then be generated from the private key. Generating a private key from a random number. The first and most important step in generating keys is to find a secure source of entropy, or randomness. Creating an Ethereum private key essentially involves picking a number between 1 and 2. The exact method you use to pick that number does not matter as long as it is not predictable or deterministic. Ethereum software uses the underlying operating system's random number generator to produce 256 random bits. Usually, the OS random number generator is initialized by a human source of randomness, which is why you may be asked to wiggle your mouse around for a few seconds, or press random keys on your keyboard. An alternative could be cosmic radiation noise on the computer's microphone channel. More precisely, a private key can be any non-zero number up to a very large number slightly less than 2, a huge 78-digit number, roughly 1.158*10. The exact number shares the first 38 digits with 2 and is defined as the order of the elliptic curve used in Ethereum. See elliptic curve cryptography explained. To create a private key, we randomly pick a 256-bit number and check that it is within the valid range. In programming terms, this is usually achieved by feeding an even larger string of random bits, collected from a cryptographically secure source of randomness, into a 256-bit hash algorithm such as Cupcake 256 or SHA-256. Both of which will conveniently produce a 256-bit number. If the result is within the valid range, we have a suitable private key. Otherwise, we simply try again with another random number. 2 the size of Ethereum's private key space is an unfathomably large number. It is approximately 10 in decimal, that is, a number with 77 digits. For comparison, the visible universe is estimated to contain between 10 to the power of 77th and 10 to the power of 80th atoms. Therefore, at the lower range there are enough private keys to give every atom in the universe an Ethereum account. If you pick a private key randomly, there is no conceivable way anyone will ever guess it or pick it themselves. Note that the private key generation process is an offline one. It does not require any communication with the Ethereum network, or indeed any communication with anyone at all. As such, in order to pick a number that no one else will ever pick, it needs to be truly random. If you choose the number yourself, the chance that someone else will try it, and then run off with your Ether, is too high. Using a bad random number generator, like the pseudo-random rand function in most programming languages, is even worse, because it is even more obvious and even easier to replicate. Just like with passwords for online accounts, the private key needs to be unguessable. Fortunately, you never need to remember your private key, so you can take the best possible approach for picking it, namely, true randomness. Do not write your own code to create a random number or use a simple random number generator offered by your programming language. It is vital that you use a cryptographically secure pseudo-random number generator, such as CSPRNG, with a seed from a source of sufficient entropy. Study the documentation of the random number generator library you choose to make sure it is cryptographically secure. Correct implementation of the CSPRNG library is critical to the security of the keys. The following is a randomly generated private key shown in hexadecimal format, 256 bits shown as 64 hexadecimal digits, each 4 bits. Public keys. An Ethereum public key is a point on an elliptic curve, meaning it is a set of x and y coordinates that satisfy the elliptic curve equation. In simpler terms, an Ethereum public key is 2 numbers, joined together. These numbers are produced from the private key by a calculation that can only go one way. That means that it is trivial to calculate a public key if you have the private key, but you cannot calculate the private key from the public key. Math is about to happen. Don't panic. If you start to get lost at any point in the following paragraphs, you can skip the next few sections. There are many tools and libraries that will do the math for you. The public key is calculated from the private key using elliptic curve multiplication, which is practically irreversible. K equals K asterisk G, where K is the private key. G is a constant point called the generator point, K is the resulting public key, and asterisk is the special elliptic curve multiplication operator. Note that elliptic curve multiplication is not like normal multiplication. It shares functional attributes with normal multiplication, but that is about it. For example, the reverse operation, which would be division for normal numbers, known as finding the discrete logarithm, I.e. Calculating K if you know K is as difficult as trying all possible values of K, a brute force search that will likely take more time than this universe will allow for. In simpler terms, arithmetic on the elliptic curve is different from regular integer arithmetic. A point, G, can be multiplied by an integer, K, to produce another point, K. But there is no such thing as division, so it is not possible to simply divide the public key K by the point G to calculate the private key K. This is the one-way mathematical function described in public key cryptography and cryptocurrency. Elliptic curve multiplication is a type of function that cryptographers call a one-way function. It is easy to do in one direction, multiplication, and impossible to do in the reverse direction, division. The owner of the private key can easily create the public key and then share it with the world, knowing that no one can reverse the function and calculate the private key from the public key. This mathematical trick becomes the basis for unforgeable and secure digital signatures that prove ownership of Ethereum funds and control of contracts. Before we demonstrate how to generate a public key from a private key, let's look at elliptic curve cryptography in a bit more detail. Elliptic curve cryptography explained. Elliptic curve cryptography is a type of asymmetric or public key cryptography based on the discrete logarithm problem as expressed by addition and multiplication on the points of an elliptic curve. A visualization of an elliptic curve is an example of an elliptic curve, similar to that used by Ethereum. Ethereum uses the exact same elliptic curve, called SEC256K1, as Bitcoin. That makes it possible to reuse many of the elliptic curve libraries and tools from Bitcoin. Ethereum uses a specific elliptic curve and set of mathematical constants, as defined in a standard called SEC256K1, established by the U.S. National Institute of Standards and Technology, NIST. The SEC256K1 curve is defined by the following function, which produces an elliptic curve. The mod p, modulo prime number p, indicates that this curve is over a finite field of prime order p, also written as math fp where p equals 2 to 2, 2 to 2, 2 to 2, 2 to 1, which is a very large prime number. Because this curve is defined over a finite field of prime order instead of over the real numbers, it looks like a pattern of dots scattered in 2 dimensions, which makes it difficult to visualize. However, the math is identical to that of an elliptic curve over real numbers. As an example, elliptic curve cryptography, visualizing an elliptic curve over f, p, with p equals 17 shows the same elliptic curve over a much smaller finite field of prime order 17, showing a pattern of dots on a grid. The SEC256K1 Ethereum elliptic curve can be thought of as a much more complex pattern of dots on an unfathomably large grid. So, for example, the following is a point Q with coordinates, x, y, that is a point on the SEC256K1 curve. Q equals 497903908252493844860331443559168646076160835201016386814003. Example 1 shows how you can check this yourself using Python. The variables x and y are the coordinates of the point Q, as in the preceding example. The variable p is the prime order of the elliptic curve, the prime that is used for all the modulo operations. The last line of Python is the elliptic curve equation, the percent operator in Python is the modulo operator. If x and y are indeed the coordinates of a point on the elliptic curve, then they satisfy the equation and the result is 0. 0L is a long integer with value 0. Try it yourself, by typing Python on a command line and copying each line, after the prompt, from the listing. Using Python to confirm that this point is on the elliptic curve. Python 3.4.0, default, March 3rd, elliptic curve arithmetic operations. A lot of elliptic curve math looks and works very much like the integer arithmetic we learned at school. Specifically, we can define an addition operator, which instead of jumping along the number line is jumping to other points on the curve. Once we have the addition operator, we can also define multiplication of a point in a whole number, which is equivalent to repeated addition. Elliptic curve addition is defined such that given 2 points p1 and p2 on the elliptic curve, there is a third point p3 equals p1 plus p2, also on the elliptic curve. Geometrically, this third point p3 is calculated by drawing a line between p1 and p2. This line will intersect the elliptic curve in exactly one additional place, amazingly. Call this point p3 equals x, y. Then reflect in the x-axis to get p3 equals x, y. If p1 and p2 are the same point, the line between p1 and p2 should extend to be the tangent to the curve at this point p1. This tangent will intersect the curve at exactly one new point. You can use techniques from calculus to determine the slope of the tangent line. Curiously, these techniques work, even though we are restricting our interest to points on the curve with 2 integer coordinates. In elliptic curve math, there is also a point called the point at infinity, which roughly corresponds to the role of the number 0 in addition. On computers, it's sometimes represented by x equals y equals 0, which doesn't satisfy the elliptic curve equation, but it's an easy separate case that can be checked. There are a couple of special cases that explain the need for the point at infinity. In some cases, example if p1 and p2 have the same x values but different y values, the line will be exactly vertical, in which case p3 equals the point at infinity. If p1 is the point at infinity, then p1 plus p2 equals p2. Similarly, if p2 is the point at infinity, then p1 plus p2 equals p1. This shows how the point at infinity plays the role that 0 plays in normal arithmetic. It turns out that plus is associative, which means that a plus b equals a plus b plus c. That means we can write a plus b plus c, without parentheses, without ambiguity. Now that we have defined addition, we can define multiplication in the standard way that extends addition. For a point p on the elliptic curve, if k is a whole number, then k asterisk p equals p plus p plus p plus p, k times. Note that k is sometimes, perhaps confusingly, called an exponent in this case. Generating a public key. Starting with a private key in the form of a randomly generated number k, we multiply it by a predetermined point on the curve called the generator point g to produce another point somewhere else on the curve, which is the corresponding public key k. K equals k asterisk g. The generator point is specified as part of the SEC256K1 standard. It is the same for all implementations of SEC256K1, and all keys derived from that curve use the same point g. Because the generator point is always the same for all Ethereum users. A private key k multiplied with g will always result in the same public key k. The relationship between k and k is fixed, but can only be calculated in one direction. From k to k. That's why an Ethereum address, derived from k, can be shared with anyone and does not reveal the user's private key, k. As we described in the previous section, the multiplication of k asterisk g is equivalent to repeated addition, so g plus g plus g plus g, repeated k times. In summary, to produce a public key k from a private key k, we add the generator point g to itself, k times. Tip. A private key can be converted into a public key, but a public key cannot be converted back into a private key, because the math only works one way. Let's apply this calculation to find the public key for the specific private key we showed you in private keys. Example private key to public key calculation k equals f8 f8 a2 f4 3 c8 3 7. A cryptographic library can help us calculate k, using elliptic curve multiplication. The resulting public key k is defined as the point k equals x, y, where x equals 6E145xF1033. In Ethereum you may see public keys represented as a serialization of 130 hexadecimal characters, 65 bytes. This is adopted from a standard serialization format proposed by the Industry Consortium Standards for Efficient Cryptography Group, SECG, documented in Standards for Efficient Cryptography, SEC1. The standard defines 4 possible prefixes that can be used to identify points on an elliptic curve, listed in serialized EC public key prefixes. Prefix meaning length, bytes counting prefix. 0x00. Point at infinity. 1. 0x04. Uncompressed point. 65. 0x02. Compressed point with even y. 33. 0x03. Compressed point with odd y. 33. Ethereum only uses uncompressed public keys, therefore the only prefix that is relevant is hex 04. The serialization concatenates the x and y coordinates of the public key. 04 plus x coordinate, 32 bytes / 64 hex, plus y coordinate, 32 bytes / 64 hex. Therefore, the public key we calculated earlier is serialized as 046E145XF1033D2 elliptic curve libraries. There are a couple of implementations of the SEC256K1 elliptic curve that are used in cryptocurrency-related projects. OpenSSL. The OpenSSL library offers a comprehensive set of cryptographic primitives, including a full implementation of SEC256K1. For example, to derive the public key, the function ECPOINTMUL can be used. libsec256K1. Bitcoin Core's libsec256K1 is a C-language implementation of the SEC256K1 elliptic curve and other cryptographic primitives. It was written from scratch to replace OpenSSL in Bitcoin Core software, and is considered superior in both performance and security. Cryptographic hash functions. Cryptographic hash functions are used throughout Ethereum. In fact, hash functions are used extensively in almost all cryptographic systems, a fact captured by cryptographer Bruce Schneier, who said, "Much more than encryption algorithms, one-way hash functions are the workhorses of modern cryptography." In this section we will discuss hash functions, explore their basic properties, and see how those properties make them so useful in so many areas of modern cryptography. We address hash functions here because they are part of the transformation of Ethereum public keys into addresses. They can also be used to create digital fingerprints, which aid in the verification of data. In simple terms, a hash function is any function that can be used to map data of arbitrary size to data of fixed size. The input to a hash function is called a preimage, the message, or simply the input data. The output is called the hash. Cryptographic hash functions are a special subcategory that have specific properties that are useful to secure platforms, such as Ethereum. A cryptographic hash function is a one-way hash function that maps data of arbitrary size to a fixed size string of bits. The one-way nature means that it is computationally infeasible to recreate the input data if one only knows the output hash. The only way to determine a possible input is to conduct a brute force search, checking each candidate for a matching output. Given that the search space is virtually infinite, it is easy to understand the practical impossibility of the task. Even if you find some input data that creates a matching hash, it may not be the original input data. Hash functions are many-to-one functions. Finding two sets of input data that hash to the same output is called finding a hash collision. Roughly speaking, the better the hash function, the rarer hash collisions are. For Ethereum, they are effectively impossible. Determinism. A given input message always produces the same hash output. Verifiability. Computing the hash of a message is efficient. Linear complexity. Non-correlation. A small change to the message, example a 1-bit change, should change the hash output so extensively that it cannot be correlated to the hash of the original message. Irreversibility. Computing the message from its hash is infeasible, equivalent to a brute force search through all possible messages. Collision protection. It should be infeasible to calculate two different messages that produce the same hash output. Resistance to hash collisions is particularly important for avoiding digital signature forgery in Ethereum. The combination of these properties make cryptographic hash functions useful for a broad range of security applications, including Ethereum's cryptographic hash function, Cupcake256. Ethereum uses the Cupcake256 cryptographic hash function in many places. Cupcake256 was designed as a candidate for the SHA-3 cryptographic hash function competition held in 2007 by the National Institute of Standards and Technology. Cupcake was the winning algorithm, which became standardized as Federal Information Processing Standard, FIPS, 202 in 2015. However, during the period when Ethereum was developed, the NIST standardization was not yet finalized. NIST adjusted some of the parameters of Cupcake after the completion of the standards process, allegedly to improve its efficiency. This was occurring at the same time as heroic whistleblower Edward Snowden revealed documents that imply that NIST may have been improperly influenced by the National Security Agency to intentionally weaken the dual ECD-RBG random number generator standard, effectively placing a backdoor in the standard random number generator. The result of this controversy was a backlash against the proposed changes and a significant delay in the standardization of SHA-3. At the time, the Ethereum Foundation decided to implement the original Cupcake algorithm, as proposed by its inventors, rather than the SHA-3 standard as modified by NIST. While you may see SHA-3 mentioned throughout Ethereum documents and code, many if not all of those instances actually refer to Cupcake256, not the finalized FIPS 202 SHA-3 standard. The implementation differences are slight, having to do with padding parameters, but they are significant in that Cupcake256 produces different hash outputs from FIPS 202 SHA-3 for the same input. Which hash function am I using? How can you tell if the software library you are using implements FIPS 202 SHA-3 or Cupcake256, if both might be called SHA-3? An easy way to tell is to use a test vector, an expected output for a given input. The test most commonly used for a hash function is the empty input. If you run the hash function with an empty string as input, you should see the following results. Cupcake256 equals C5D2460186F7233. Regardless of what the function is called, you can test it to see whether it is the original Cupcake256 or the final NIST standard FIPS 202 SHA-3 by running this simple test. Remember, Ethereum uses Cupcake256, even though it is often called SHA-3 in the code. Due to the confusion created by the difference between the hash function used in Ethereum, Cupcake256, and the finalized standard, FIPS 202 SHA-3, there is an effort underway to rename all instances of SHA-3 in all code, opcodes, and libraries to Cupcake256. See EIP 59 for details. Next, let's examine the first application of Go-eth 256 in Ethereum, which is to produce Ethereum addresses from public keys. Ethereum addresses. Ethereum addresses are unique identifiers that are derived from public keys or contracts using the Go-eth 256 one-way hash function. In our previous examples, we started with a private key and used elliptic curve multiplication to derive a public key. It is worth noting that the public key is not formatted with the prefix. It is worth noting that the public key is not formatted with the prefix hex 04 when the address is calculated. Most often you will see Ethereum addresses with the prefix 0x that indicates they are hexadecimal encoded, like this. Ethereum Cryptography. One of Ethereum's foundational technologies. One of Ethereum. Cryptography. One of Ethereum's foundational technologies is cryptography, which is a branch of mathematics used extensively in computer security. And we keep only the last 20 bytes, least significant bytes, which Most often you will see Ethereum addresses with the prefix 0x that indicates they are hexadecimal encoded, like this. Ethereum address formats. Ethereum addresses are hexadecimal numbers, identifiers derived from the last 20 bytes of the Go-eth 256 hash of the public key. Unlike Bitcoin addresses, which are encoded in the user interface of all clients to include a built-in checksum to protect against mistyped addresses, Ethereum addresses are presented as raw hexadecimal without any checksum. The rationale behind that decision was that Ethereum addresses would eventually be hidden behind abstractions, such as name services, at higher layers of the system and that checksums should be added at higher layers if necessary. In reality, these higher layers were developed too slowly and this design choice led to a number of problems in the early days of the ecosystem, including the loss of funds due to mistyped addresses and input validation errors. Furthermore, because Ethereum name services were developed slower than initially expected, alternative encodings were adopted very slowly by wallet developers. We'll look at a few of the encoding options next. Inter-Exchange Client Address Protocol. The Inter-Exchange Client Address Protocol, ICAP, is an Ethereum address encoding that is partly compatible with the International Bank Account Number, IBAN, encoding, offering a versatile, checksummed, and interoperable encoding for Ethereum addresses. ICAP addresses can encode Ethereum addresses or common names registered with an Ethereum name registry. You can read more about ICAP on the Ethereum wiki. IBAN is an international standard for identifying bank account numbers, mostly used for wire transfers. It is broadly adopted in the European Single Euro Payments Area, SEPA, and beyond. IBAN is a centralized and heavily regulated service. ICAP is a decentralized but compatible implementation for Ethereum addresses. An IBAN consists of a string of up to 34 alphanumeric characters, case-insensitive, comprising a country code, checksum, and bank account identifier, which is country-specific. ICAP uses the same structure by introducing a non-standard country code, XE, that stands for Ethereum, followed by a 2-character checksum and 3 possible variations of an account identifier. Direct. Basic. Indirect. We can use the help. We can use the helpeth command line tool to create ICAP addresses. You can get helpeth by installing it with. If you don't have NPM, you may have to install Node.js first, which you can do by following the instructions at https://nodejs.org. Now that we have helpeth, let's try creating an ICAP address with our example private key, prefixed with 0x and passed as a parameter to helpeth. $helpeth k.ales \p0x f8f8a2f xe60 homi cdxsv. The helpeth command constructs a hexadecimal Ethereum address as well as an ICAP address for us. The ICAP address for our example key is. Because our example Ethereum address happens to start with a 0 byte, it can be encoded using the direct ICAP encoding method that is valid in IBAN format. You can tell because it is 33 characters long. If our address did not start with a 0, it would be encoded with the basic encoding, which would be 35 characters long and invalid as an IBAN. The chances of any Ethereum address starting with a 0 byte are 1 in 256. To generate one like that, it will take on average 256 attempts with 256 different random private keys before we find one that works as an IBAN-compatible direct encode, hex encoding with checksum and capitalization, EIP 55. Due to the slow deployment of ICAP and name services, a standard was proposed by Ethereum Improvement Proposal 55, EIP 55. EIP55 offers a backward-compatible checksum for Ethereum addresses by modifying the capitalization of the hexadecimal address. The idea is that Ethereum addresses are case-insensitive and all wallets are supposed to accept Ethereum addresses expressed in capital or lowercase characters, without any difference in interpretation. By modifying the capitalization of the alphabetic characters in the address, we can convey a checksum that can be used to protect the integrity of the address against typing or reading mistakes. Wallets that do not support EIP55 checksums simply ignore the fact that the address contains mixed capitalization, but those that do support it can validate it and detect errors with a 99.986% accuracy. Can you tell the difference? Some of the alphabetic A, F characters from the hexadecimal encoding alphabet are now capital, while others are lowercase. EIP55 is quite simple to implement. We take the cupcake256 hash of the lowercase hexadecimal address. This hash acts as a digital fingerprint of the address, giving us a convenient checksum. Any small change in the input, the address, should cause a big change in the resulting hash, the checksum, allowing us to detect errors effectively. The hash of our address is then encoded in the capitalization of the address itself. Let's break it down, step by step. Cupcake256, 001D3F1F8275528E111, address, 001D3F1F8275528E11, our address contains an alphabetic character D in the fourth position. The fourth character of the hash is 6, which is less than 8. So, we leave the D lowercase. The next alphabetic character in our address is F, in the sixth position. The sixth character of the hexadecimal hash is C, which is greater than 8. Therefore, we capitalize the F in the address, and so on. As you can see, we only use the first 20 bytes, 40 hex characters, of the hash as a checksum, since we only have 20 bytes, 40 hex characters, in the address to capitalize appropriately. Check the resulting mixed capitals address yourself and see if you can tell which characters were capitalized and which characters they correspond to in the address hash. Address, 001D3F1F8, detecting an error in an EIP55 encoded address. Now, let's look at how EIP55 addresses will help us find an error. Let's assume we have printed out an Ethereum address. Now let's make a basic mistake in reading that address. The character before the last one is a capital F. For this example, let's assume we misread that as a capital E, and we type the following, incorrect, address into our wallet. Fortunately, our wallet is EIP55 compliant. It notices the mixed capitalization and attempts to validate the address. It converts it to lowercase, and calculates the checksum hash. Cupcake2, as you can see, even though the address has only changed by one character, in fact, only one bit, as E and F are one bit apart, the hash of the address has changed radically. That's the property of hash functions that makes them so useful for checksums. It's all wrong. Several of the alphabetic characters are incorrectly capitalized. Remember that the capitalization is the encoding of the correct checksum. The capitalization of the address we input doesn't match the checksum just calculated, meaning something has changed in the address, and an error has been introduced. Conclusions. In this chapter we provided a brief survey of public key cryptography and focused on the use of public and private keys in Ethereum and the use of cryptographic tools, such as hash functions, in the creation and verification of Ethereum addresses. We also looked at digital signatures and how they can demonstrate ownership of a private key without revealing that private key. In Wallets chapter, we will put these ideas together and look at how wallets can be used to manage collections of keys. Wallets. At a high level, a wallet is a software application that serves as the primary user interface to Ethereum. The wallet controls access to a user's money, managing keys and addresses, tracking the balance, and creating and signing transactions. In addition, some Ethereum wallets can also interact with contracts, such as ERC20 tokens. More narrowly, from a programmer's perspective, the word wallet refers to the system used to store and manage a user's keys. Every wallet has a key management component. For some wallets, that's all there is. Other wallets are part of a much broader category, that of browsers, which are interfaces to Ethereum-based decentralized applications, or dApps, which we will examine in more detail in Decentralized Applications cap. There are no clear lines of distinction between the various categories that are CONF-lated under the term wallet. In this chapter we will look at wallets as containers for private keys, and as systems for managing these keys. Wallet technology overview. Wallet Technology Overview. In this section we summarize the various technologies used to construct user-friendly, secure, and flexible Ethereum wallets. One key consideration in designing wallets is balancing convenience and privacy. The most convenient Ethereum wallet is one with a single private key and address that you reuse for everything. Unfortunately, such a solution is a privacy nightmare, as anyone can easily track and correlate all your transactions. Using a new key for every transaction is best for privacy, but becomes very difficult to manage. The correct balance is difficult to achieve, but that's why good wallet design is paramount. A common misconception about Ethereum is that Ethereum wallets contain Ether or tokens. In fact, very strictly speaking, the wallet holds only keys. The Ether or other tokens are recorded on the Ethereum blockchain. Users control the tokens on the network by signing transactions with the keys in their wallets. In a sense, an Ethereum wallet is a keychain. Having said that, given that the keys held by the wallet are the only things that are needed to transfer Ether or tokens to others, in practice this distinction is fairly irrelevant. Where the difference does matter is in changing one's mindset from dealing with the centralized system of conventional banking, where only you, and the bank, can see the money in your account. And you only need convince the bank that you want to move funds to make a transaction, to the decentralized system of blockchain platforms, where everyone can see the Ether balance of an account. Although they probably don't know the account's owner, and everyone needs to be convinced the owner wants to move funds for a transaction to be enacted. In practice this means that there is an independent way to check an account's balance, without needing its wallet. Moreover, you can move your account handling from your current wallet to a different wallet, if you grow to dislike the wallet app you started out using. Ethereum wallets contain keys, not Ether, or tokens. Wallets are like keychains containing pairs of private and public keys. Users sign transactions with the private keys, thereby proving they own the Ether. The Ether is stored on the blockchain. There are two primary types of wallets, distinguished by whether the keys they contain are related to each other or not. The first type is a non-deterministic wallet, where each key is independently generated from a different random number. The keys are not related to each other. This type of wallet is also known as a JBOK wallet, from the phrase, just a bunch of keys. The second type of wallet is a deterministic wallet, where all the keys are derived from a single master key, known as the seed. All the keys in this type of wallet are related to each other and can be generated again if one has the original seed. There are a number of different key derivation methods used in deterministic wallets. The most commonly used derivation method uses a tree-like structure, as described in hierarchical deterministic wallets, BIP32/BIP44. To make deterministic wallets slightly more secure against data loss accidents, such as having your phone stolen or dropping it in the toilet. The seeds are often encoded as a list of words, in English or another language, for you to write down and use in the event of an accident. These are known as the wallet's mnemonic code words. Of course, if someone gets hold of your mnemonic code words, then they can also recreate your wallet and thus gain access to your Ether and smart contracts. As such, be very, very careful with your recovery word list. Never store it electronically, in a file, on your computer or phone. Write it down on paper and store it in a safe and secure place. Non-deterministic, random, wallets. In the first Ethereum wallet, produced for the Ethereum presale, each wallet file stored a single randomly generated private key. Such wallets are being replaced with deterministic wallets because these old-style wallets are in many ways inferior. For example, it is considered good practice to avoid Ethereum address reuse as part of maximizing your privacy while using Ethereum IE, to use a new address, which needs a new private key, every time you receive funds. You can go further and use a new address for each transaction, although this can get expensive if you deal a lot with tokens. To follow this practice, a non-deterministic wallet will need to regularly increase its list of keys, which means you will need to make regular backups. If you ever lose your data, disk failure, drink accident, phone stolen, before you've managed to back up your wallet, you will lose access to your funds and smart contracts. The Type 0 non-deterministic wallets are the hardest to deal with, because they create a new wallet file for every new address in a just-in-time manner. Nevertheless, many Ethereum clients, including Go-eth, use a keys-tor file, which is a JSON encoded file that contains a single, randomly generated, private key, encrypted by a passphrase for extra security. The JSON file's contents look like this. Address, 001D3F1. The keys-tor format uses a key derivation function, KDF, also known as a password stretching algorithm, which protects against brute force, dictionary, and rainbow table attacks. In simple terms, the private key is not encrypted by the passphrase directly. Instead, the passphrase is stretched by repeatedly hashing it. The hashing function is repeated for 262,144 rounds, which can be seen in the keys-tor JSON as the parameter crypto.caveparams.n. An attacker trying to brute force the passphrase would have to apply 144 rounds of hashing for every attempted passphrase, which slows down the attack sufficiently to make it infeasible for passphrase of sufficient complexity and length. There are a number of software libraries that can read and write the keys-tor format, such as the JavaScript library Ethereum. The use of non-deterministic wallets is discouraged for anything other than simple tests. They are too cumbersome to back up and use for anything but the most basic of situations. Instead, use an industry standard. Deterministic, seeded, wallets. Deterministic or seeded wallets are wallets that contain private keys that are all derived from a single master key, or seed. The seed is a randomly generated number that is combined with other data, such as an index number or chain code, see extended public and private keys, to derive any number of private keys. In a deterministic wallet, the seed is sufficient to recover all the derived keys, and therefore a single backup, at creation time, is sufficient to secure all the funds and smart contracts in the wallet. The seed is also sufficient for a wallet export or import, allowing for easy migration of all the keys between different wallet implementations. This design makes the security of the seed of utmost importance, as only the seed is needed to gain access to the entire wallet. On the other hand, being able to focus security efforts on a single piece of data can be seen as an advantage. Hierarchical deterministic wallets, BIP32/BIP44. Deterministic wallets were developed to make it easy to derive many keys from a single seed. Currently, the most advanced form of deterministic wallet is the hierarchical deterministic (HD) wallet defined by Bitcoin's BIP32 standard. HD wallets contain keys derived in a tree structure, such that a parent key can derive a sequence of child keys, each of which can derive a sequence of grandchild keys, and so on. This tree structure is illustrated in HD wallet, a tree of keys generated from a single seed. HD wallets offer a few key advantages over simpler deterministic wallets. First, the tree structure can be used to express additional organizational meaning, such as when a specific branch of subkeys is used to receive incoming payments and a different branch is used to receive change from outgoing payments. Branches of keys can also be used in corporate settings, allocating different branches to departments, subsidiaries, specific functions, or accounting categories. The second advantage of HD wallets is that users can create a sequence of public keys without having access to the corresponding private keys. This allows HD wallets to be used on an insecure server or in a watch-only or receive-only capacity, where the wallet doesn't have the private keys that can spend the funds. Seeds and mnemonic codes, BIP39. There are many ways to encode a private key for secure backup and retrieval. The currently preferred method is using a sequence of words that, when taken together in the correct order, can uniquely recreate the private key. This is sometimes known as a mnemonic, and the approach has been standardized by BIP39. Today, many Ethereum wallets, as well as wallets for other cryptocurrencies, use this standard, and can import and export seeds for backup and recovery using interoperable mnemonics. In practical terms, the chance of an error when writing down the hex sequence is unacceptably high. In contrast, the list of known words is quite easy to deal with, mainly because there is a high level of redundancy in the writing of words, especially English words. If insect had been recorded by accident, it could quickly be determined, upon the need for wallet recovery, that insect is not a valid English word and that insect should be used instead. We are talking about writing down a representation of the seed because that is good practice when managing HD wallets. The seed is needed to recover a wallet in the case of data loss, whether through accident or theft, so keeping a backup is very prudent. However, the seed must be kept extremely private, so digital backups should be carefully avoided, hence the earlier advice to back up with pen and paper. In summary, the use of a recovery word list to encode the seed for an HD wallet makes for the easiest way to safely export, transcribe, record on paper, read without error, and import a private key set into another wallet. Wallet best practices. As cryptocurrency wallet technology has matured, certain common industry standards have emerged that make wallets broadly interoperable, easy to use, secure, and flexible. These standards also allow wallets to derive keys for multiple different cryptocurrencies, all from a single mnemonic. These common standards are. These standards may change or be obsolete by future developments, but for now they form a set of interlocking technologies that have become the de facto wallet standard for most blockchain platforms and their cryptocurrencies. The standards have been adopted by a broad range of software and hardware wallets, making all these wallets interoperable. A user can export a mnemonic generated in one of these wallets and import it to another wallet, recovering all keys and addresses. Some examples of software wallets supporting these standards include, listed alphabetically, Jax, MetaMask, MyCrypto, and MyEtherWallet, Mu. Examples of hardware wallets supporting these standards include Keepkey, Ledger, and Trezor. If you are implementing an Ethereum wallet, it should be built as an HD wallet, with a seed encoded as a mnemonic code for backup, following the BIP32, BIP30, mnemonic code words, BIP39. Mnemonic code words are word sequences that encode a random number used as a seed to derive a deterministic wallet. The sequence of words is sufficient to recreate the seed, and from there recreate the wallet and all the derived keys. A wallet application that implements deterministic wallets with mnemonic words will show the user a sequence of 12 to 24 words when first creating a wallet. That sequence of words is the wallet backup, and can be used to recover and recreate all the keys in the same or any compatible wallet application. As we explained earlier, mnemonic word lists make it easier for users to back up wallets, because they are easy to read and correctly transcribe. Mnemonic words are often confused with brain wallets. They are not the same. The primary difference is that a brain wallet consists of words chosen by the user, whereas mnemonic words are created randomly by the wallet and presented to the user. This important difference makes mnemonic words much more secure, because humans are very poor sources of randomness. Perhaps more importantly, using the term brain wallet suggests that the words have to be memorized, which is a terrible idea, and a recipe for not having your backup when you need it. Mnemonic codes are defined in BIP39. Note that BIP39 is one implementation of a mnemonic code standard. There is a different standard, with a different set of words, used by the Electrum Bitcoin wallet and predating BIP39. BIP39 was proposed by the company behind the Trezor hardware wallet and is incompatible with Electrum's implementation. However, BIP39 has now achieved broad industry support across dozens of interoperable implementations and should be considered the de facto industry standard. Furthermore, BIP39 can be used to produce multi-currency wallets supporting Ethereum, whereas Electrum seeds cannot. BIP39 defines the creation of a mnemonic code and seed, which we describe here in 9 steps. For clarity, the process is split into 2 parts. Steps 1 through 6 are shown in generating mnemonic words and steps 7 through 9 are shown in from mnemonic to seed. Generating mnemonic words. Mnemonic words are generated automatically by the wallet using the standardized process defined in BIP39. The wallet starts from a source of entropy, adds a checksum, and then maps the entropy to a word list. Create a cryptographically random sequence S of 128 to 256 bits. Create a checksum of S by taking the first length of S divided by 32 bits of the SHA-256 hash of S. Add the checksum to the end of the random sequence S. Divide the sequence and checksum concatenation into sections of 11 bits. Map each 11-bit value to a word from the predefined dictionary of 2048 words. Create the mnemonic code from the sequence of words, maintaining the order. Generating entropy and encoding as mnemonic words shows how entropy is used to generate mnemonic words. Mnemonic codes, entropy and word length shows the relationship between the size of the entropy data and the length of mnemonic codes in words. Entropy, bits, checksum, bits, entropy plus checksum, bits, mnemonic length, words. 128. 4. 132. 12. 160. 5. 165. 15. 192. 6. From mnemonic to seed. The mnemonic words represent entropy with a length of 128 to 256 bits. The entropy is then used to derive a longer, 512-bit, seed through the use of the key stretching function pbkdf2. The seed produced is used to build a deterministic wallet and derive its keys. The key stretching function takes two parameters, the mnemonic and assault. The purpose of assault in a key stretching function is to make it difficult to build a lookup table enabling a brute force attack. In the BIP39 standard, the salt has another purpose. It allows the introduction of a passphrase that serves as an additional security factor protecting the seed, as we will describe in more detail in optional passphrase in BIP39. The process described in steps 7 through 9 continues from the process described in the previous section. The first parameter to the pbkdf2 key stretching function is the mnemonic produced in step 6. The second parameter to the pbkdf2 key stretching function is assault. The salt is composed of the string constant mnemonic concatenated with an optional user-supplied passphrase. pbkdf2 stretches the mnemonic and salt parameters using 2048 rounds of hashing with the HMAC SHA-512 algorithm, producing a 512-bit value as its final output. That 512-bit value is the seed. From mnemonic to seed shows how a mnemonic is used to generate a seed. Figure 3. From mnemonic to seed. Note. The key stretching function, with its 2048 rounds of hashing, is a somewhat effective protection against brute force attacks against the mnemonic or the passphrase. It makes it costly, in computation, to try more than a few thousand passphrase and mnemonic combinations, while the number of possible derived seeds is vast, 2, or about 10, far bigger than the number of atoms in the visible universe, about 10. Tables hashtag mnemonic 128 nopass, hashtag mnemonic 128 opus, and hashtag mnemonic 256 nopass show some examples of mnemonic codes and the seeds they produce. Entropy input, 128 bits. 0C1E24E59177797E144D45F14E1A1A. Mnemonic, 12 words. Army van defense carry jealous true garbage claim echo media make crunch. Passphrase. None. Seed, 512 bits. 5B56C, optional passphrase in BIP39. The BIP39 standard allows the use of an optional passphrase in the derivation of the seed. If no passphrase is used, the mnemonic is stretched with a salt consisting of the constant string mnemonic, producing a specific 512-bit seed from any given mnemonic. If a passphrase is used, the stretching function produces a different seed from that same mnemonic. In fact, given a single mnemonic, every possible passphrase leads to a different seed. Essentially, there is no wrong passphrase. All passphrases are valid and they all lead to different seeds, forming a vast set of possible uninitialized wallets. The set of possible wallets is so large, too, that there is no practical possibility of brute forcing or accidentally guessing one that is in use, as long as the passphrase has sufficient complexity and length. There are no wrong passphrases in BIP39. Every passphrase leads to some wallet, which unless previously used will be empty. A second factor, something memorized, that makes a mnemonic useless on its own, protecting mnemonic backups from compromise by a thief. A form of plausible deniability or duress wallet, where a chosen passphrase leads to a wallet with a small amount of funds, used to distract an attacker from the real wallet that contains the majority of funds. If the wallet owner is incapacitated or dead and no one else knows the passphrase, the seed is useless and all the funds stored in the wallet are lost forever. Conversely, if the owner backs up the passphrase in the same place as the seed, it defeats the purpose of a second factor. While passphrases are very useful, they should only be used in combination with a carefully planned process for backup and recovery, considering the possibility of heirs surviving the owner being able to recover the cryptocurrency. Working with mnemonic codes. Python mnemonic. The reference implementation of the standard by the Satoshi Labs team that proposed BIP39, in Python. Consenzi/Eth Wallet. Lightweight JS Ethereum wallet for nodes in browser, with BIP39. npm/BIP39. JavaScript implementation of Bitcoin BIP39, mnemonic code for generating deterministic keys. There is also a BIP39 generator implemented in a standalone web page. A BIP39 generator is a standalone web page, which is extremely useful for testing and experimentation. The mnemonic code converter generates mnemonics, seeds, and extended private keys. It can be used offline in a browser, or accessed online. Creating an HD wallet from the seed. HD wallets are created from a single root seed, which is a 128-256- or 512-bit random number. Most commonly, the seed is generated from a mnemonic as detailed in the previous section. Every key in the HD wallet is deterministically derived from this root seed, which makes it possible to recreate the entire HD wallet from that seed in any compatible HD wallet. This makes it easy to export, backup, restore, and import HD wallets containing thousands or even millions of keys by transferring just the mnemonic from which the root seed is derived. HD wallets, BIP32, and paths, BIP43/44. Most HD wallets follow the BIP32 standard, which has become a de facto industry standard for deterministic key generation. We won't be discussing all the details of BIP32 here, only the components necessary to understand how it is used in wallets. The main important aspect is the tree-like hierarchical relationships that it is possible for the derived keys to have, as you can see in HD wallet, a tree of keys generated from a single seed. It's also important to understand the ideas of extended keys and hardened keys, which are explained in the following sections. There are dozens of interoperable implementations of BIP32 offered in many software libraries. These are mostly designed for Bitcoin wallets, which implement addresses in a different way, but share the same key derivation implementation as Ethereum's BIP32 compatible wallets. Use one designed for Ethereum, or adapt one from Bitcoin by adding an Ethereum address encoding library. There is also a BIP32 generator implemented as a standalone web page that is very useful for testing and experimentation with BIP32. The standalone BIP32 generator is not an HTTPS site. That's to remind you that the use of this tool is not secure. It is only for testing. You should not use the keys produced by this site with real funds. Extended public and private keys. In BIP32 terminology, keys can be extended. With the right mathematical operations, these extended parent keys can be used to derive child keys, thus producing the hierarchy of keys and addresses described earlier. A parent key doesn't have to be at the top of the tree. It can be picked out from anywhere in the tree hierarchy. Extending a key involves taking the key itself and appending a special chain code to it. A chain code is a 256-bit binary string that is mixed with each key to produce child keys. A very useful characteristic of HD wallets is the ability to derive child public keys from parent public keys, without having the private keys. This gives us two ways to derive a child public key, either directly from the child private key, or from the parent public key. An extended public key can be used, therefore, to derive all of the public keys, and only the public keys, in that branch of the HD wallet structure. This shortcut can be used to create very secure public key only deployments, where a server or application has a copy of an extended public key, but no private keys whatsoever. That kind of deployment can produce an infinite number of public keys and Ethereum addresses, but cannot spend any of the money sent to those addresses. Meanwhile, on another, more secure server, the extended private key can derive all the corresponding private keys to sign transactions and spend the money. One common application of this method is to install an extended public key on a web server that serves an e-commerce application. The web server can use the public key derivation function to create a new Ethereum address for every transaction, example for a customer shopping cart, and will not have any private keys that would be vulnerable to theft. Without HD wallets, the only way to do this is to generate thousands of Ethereum addresses on a separate secure server and then preload them on the e-commerce server. That approach is cumbersome and requires constant maintenance to ensure that the server doesn't run out of keys, hence the preference to use extended public keys from HD wallets. Another common application of this solution is for cold storage or hardware wallets. In that scenario, the extended private key can be stored in a hardware wallet, while the extended public key can be kept online. The user can create and receive addresses at will, while the private keys are safely stored offline. To spend the funds, the user can use the extended private key in an offline signing Ethereum client, or sign transactions on the hardware wallet device. Hardened child key derivation. The ability to derive a branch of public keys from an extended public key, or SPUB, is very useful, but it comes with a potential risk. Access to an SPUB does not give access to child private keys. However, because the SPUB contains the chain code used to derive child public keys from the parent public key, if a child private key is known, or somehow leaked, it can be used with the chain code to derive all the other child private keys. A single leaked child private key, together with a parent chain code, reveals all the private keys of all the children. Worse, the child private key together with a parent chain code can be used to deduce the parent private key. To counter this risk, HD wallets use an alternative derivation function called hardened derivation, which breaks the relationship between parent public key and child chain code. The hardened derivation function uses the parent private key to derive the child chain code, instead of the parent public key. This creates a firewall in the parent/child sequence, with a chain code that cannot be used to compromise a parent or sibling private key. In simple terms, if you want to use the convenience of an SPUB to derive branches of public keys without exposing yourself to the risk of a leaked chain code, you should derive it from a hardened parent, rather than a normal parent. Best practice is to have the level 1 children of the master keys always derived by hardened derivation, to prevent compromise of the master keys. Index numbers for normal and hardened derivation. It is clearly desirable to be able to derive more than one child key from a given parent key. To manage this, an index number is used. Each index number, when combined with a parent key using the special child derivation function, gives a different child key. The index number used in the BIP32 parent-to-child derivation function is a 32-bit integer. To easily distinguish between keys derived through the normal, unhardened, derivation function versus keys derived through hardened derivation, this index number is split into two ranges. Index numbers between 0 and 2 to 1, 0x0 to 0x7ffffff, are used only for normal derivation. Index numbers between 2 and 2 to 1, 0x8 0000000 to 0xffffff, are used only for hardened derivation. Therefore, if the index number is less than 2, the child is normal, whereas if the index number is equal to or above 2, the child is hardened. To make the index numbers easier to read and display, the index numbers for hardened children are displayed starting from 0, but with a prime symbol. The first normal child key is therefore displayed as 0, whereas the first hardened child, index 0x8000000, is displayed as 0. In sequence, then, the second hardened key would have index of 0x800000001 and would be displayed as 1, and so on. When you see an HD wallet index I, that means 2 plus I. HD wallet key identifier, path. Keys in an HD wallet are identified using a path naming convention, with each level of the tree separated by a / character. See HD wallet path examples. Private keys derived from the master private key start with M. Public keys derived from the master public key start with M. Therefore, the first child private key of the master private key is M/0. The first child public key is M/0. The second grandchild of the first child is M/0/1, and so on. The ancestry of a key is read from right to left, until you reach the master key from which it was derived. For example, identifier M/X/Y/Z describes the key that is the ZTH child of key M/X/Y, which is the YTH child of key M/X, which is the XTH child of M. HD path key described. M/0. The first, 0, child private key of the master private key, M. M/0/0. The HD wallet tree structure is tremendously flexible. The flip side of this is that it also allows for unbounded complexity. Each parent extended key can have 4 billion children, 2 billion normal children and 2 billion hardened children. Each of those children can have another 4 billion children, and so on. The tree can be as deep as you want, with a potentially infinite number of generations. With all that potential, it can become quite difficult to navigate these very large trees. 2bips offer a way to manage this potential complexity by creating standards for the structure of HD wallet trees. BIP43 proposes the use of the first hardened child index as a special identifier that signifies the purpose of the tree structure. Based on BIP43, an HD wallet should use only one level 1 branch of the tree, with the index number defining the purpose of the wallet by identifying the structure and namespace of the rest of the tree. More specifically, an HD wallet using only branch M/I/ is intended to signify a specific purpose, and that purpose is identified by index number I. Extending that specification, BIP44 proposes a multi-currency multi-account structure signified by setting the purpose number to 44. All HD wallets following the BIP44 structure are identified by the fact that they only use one branch of the tree, M/44/*. BIP44 specifies the structure as consisting of 5 predefined tree levels. M/purpose/cointype/account/change/address index. The first level, purpose, is always set to 44. The second level, coin type, specifies the type of cryptocurrency coin, allowing for multi-currency HD wallets where each currency has its own subtree under the second level. There are several currencies defined in a standards document called SLIP 0044. For example, Ethereum is M/44/60, Ethereum Classic is M/44/61, Bitcoin is M/44/0, and testnet for all currencies is M/44/1. The third level of the tree is account, which allows users to subdivide their wallets into separate logical sub-accounts for accounting or organizational purposes. For example, an HD wallet might contain 2 Ethereum accounts, M/44/60/0 and M/44/60/1. Each account is the root of its own subtree. Because BIP44 was created originally for Bitcoin, it contains a quirk that isn't relevant in the Ethereum world. On the fourth level of the path, change, an HD wallet has 2 subtrees, one for creating receiving addresses and one for creating change addresses. Only the receive path is used in Ethereum, as there is no necessity for a change address like there is in Bitcoin. Note that whereas the previous levels used hardened derivation, this level uses normal derivation. This is to allow the account level of the tree to export extended public keys for use in a non-secured environment. Usable addresses are derived by the HD wallet as children of the fourth level, making the fifth level of the tree the address index. For example, the third receiving address for Ethereum payments in the primary account would be M/44/60/0/0. BIP44 HD wallet structure. Conclusions. Wallets are the foundation of any user-facing blockchain application. They allow users to manage collections of keys and addresses. Wallets also allow users to demonstrate their ownership of Ether and authorize transactions by applying digital signatures, as we will see in this chapter. Proof of Stake, POS. Last edited at Corwin Times, January 12, 2023. Proof of Stake, POS, underlies Ethereum's consensus mechanism. Ethereum switched on its Proof of Stake mechanism in 2022 because it is more secure, less energy intensive, and better for implementing new scaling solutions compared to the previous Proof of Work architecture. Prerequisites. To better understand this page, we recommend you first read up on consensus mechanisms. What is Proof of Stake, POS? Proof of Stake underlies certain consensus mechanisms used by blockchains to achieve distributed consensus. In Proof of Work, miners prove they have capital at risk by expending energy. Ethereum uses Proof of Stake, where validators explicitly stake capital in the form of ETH into a smart contract on Ethereum. Consensus mechanisms. Last edited at Sep 1220, the term consensus mechanism is often used colloquially to refer to Proof of Stake, Proof of Work, or Proof of Authority protocols. However, these are just components in consensus mechanisms that protect against Sybil attacks. Consensus mechanisms are the complete stack of ideas, protocols, and incentives that enable a distributed set of nodes to agree on the state of a blockchain. Prerequisites. To better understand this page, we recommend you first read our introduction to Ethereum. What is consensus? By consensus, we mean that a general agreement has been reached. Consider a group of people going to the cinema. If there is no disagreement on a proposed choice of film, then a consensus is achieved. If there is disagreement, the group must have the means to decide which film to see. In extreme cases, the group will eventually split. In regard to the Ethereum blockchain, the process is formalized, and reaching consensus means that at least 66% of the nodes on the network agree on the global state of the network. What is a consensus mechanism? The term consensus mechanism refers to the entire stack of protocols, incentives, and ideas that allow a network of nodes to agree on the state of a blockchain. Ethereum uses a proof-of-stake-based consensus mechanism that derives its crypto-economic security from a set of rewards and penalties applied to capital locked by stakers. This incentive structure encourages individual stakers to operate honest validators, punishes those who don't, and creates an extremely high cost to attack the network. Then, there is a protocol that governs how honest validators are selected to propose or validate blocks, process transactions, and vote for their view of the head of the chain. In the rare situations where multiple blocks are in the same position near the head of the chain, there is a fork choice mechanism that selects blocks that make up the heaviest chain, measured by the number of validators that voted for the blocks weighted by their staked Ether balance. Some concepts are important to consensus that are not explicitly defined in code, such as the additional security offered by potential out-of-band social coordination as a last line of defense against attacks on the network. These components together form the consensus mechanism. Types of consensus mechanisms. Proof of work based. Like Bitcoin, Ethereum once used a proof of work, POW-based consensus protocol. Block creation. Miners compete to create new blocks filled with processed transactions. The winner shares the new block with the rest of the network and earns some freshly minted ETH. The race is won by the computer which is able to solve a math puzzle fastest. This produces the cryptographic link between the current block and the block that went before. Solving this puzzle is the work in proof of work. The canonical chain is then determined by a fork choice rule that selects the set of blocks that have had the most work done to mine them. Security. The network is kept secure by the fact that you'd need 51% of the network's computing power to defraud the chain. This would require such huge investments in equipment and energy, you're likely to spend more than you'd gain. More on proof of work. Proof of stake based. Ethereum now uses a proof of stake, POS, based consensus protocol. Block creation. Validators create blocks. One validator is randomly selected in each slot to be the block proposer. Their consensus client requests a bundle of transactions as an execution payload from their paired execution client. They wrap this in consensus data to form a block, which they send to other nodes on the Ethereum network. This block production is rewarded in ETH. In rare cases when multiple possible blocks exist for a single slot, or nodes hear about blocks at different times, the fork choice algorithm picks the block that forms the chain with the greatest weight of attestations, where weight is the number of validators attesting scaled by their ETH balance. Security. A proof-of-stake system is secure crypto-economically because an attacker attempting to take control of the chain must destroy a massive amount of ETH. A system of rewards incentivizes individual stakers to behave honestly, and penalties disincentivize stakers from acting maliciously. Sybil resistance and chain selection. Proof of work and proof of stake alone are not consensus protocols, but they are often referred to as such for simplicity. They are actually Sybil resistance mechanisms and block author selectors. They are a way to decide who is the author of the latest block. Another important component is the chain selection, aka fork choice, algorithm that enables nodes to pick one single correct block at the head of the chain in scenarios where multiple blocks exist in the same position. Sybil resistance measures how a protocol fares against a Sybil attack. Sybil attacks are when one user or group pretends to be many users. Resistance to this type of attack is essential for a decentralized blockchain and enables miners and validators to be rewarded equally based on resources put in. Proof of work and proof of stake protect against this by making users expend a lot of energy or put up a lot of collateral. These protections are an economic deterrent to Sybil attacks. A chain selection rule is used to decide which chain is the correct chain. Bitcoin uses the longest chain rule, which means that whichever blockchain is the longest will be the one the rest of the nodes accept as valid and work with. For proof of work chains, the longest chain is determined by the chain's total cumulative proof of work difficulty. Ethereum used to use the longest chain rule too, however, now that Ethereum runs on proof of stake it adopted an updated fork choice algorithm that measures the weight of the chain. The weight is the accumulated sum of validator votes, weighted by validator staked ether balances. Ethereum uses a consensus mechanism known as Gasper that combines Casper FFG proof of stake with the Ghost fork choice rule. Further reading. What is a blockchain consensus algorithm?
Blockchain, the hype word of 2018. But do you know how a decentralized peer-to-peer system with no authoritative figure makes decisions? The answer lies in consensus mechanisms. There are various consensus mechanisms, but they all serve the same purpose: to ensure records are true and honest. The difference is the way the consensus is reached. Here, we will explore three types of consensus mechanisms. First, let's take a look at proof of work. In a proof of work system, transaction data is stored in blocks, validated by having people solve a complicated math problem attached to it. This is typically done by powerful computers and is known as mining. A reward in the form of cryptocurrency is issued to the first miner who cracks the problem. Loss? Well, let's break it down. Imagine a group of treasure hunters trying to open a chest with a complicated lock attached to it. Figuring out the correct combination is tedious, but the first person to do so gets rewarded. Simply put, proof of work is a race to figure out the right combination on a treasure chest. Cryptocurrencies like Bitcoin and Ethereum use a proof of work mechanism. Next, we have proof of stake. Here, the creator of a new block, also known as a validator, is randomly chosen based on how much stake they commit to the network. Meaning to say, the higher the stake place, the higher the chance to be selected as a validator. Let's apply this to the treasure chest scenario. Picture a group of treasure hunters vying for a chest. The chest is rewarded based on a lottery system. To participate, each hunter has to buy lottery tickets. The more each hunter buys, the higher the chance of winning. Blockchain protocols like Cardano, Ouroboros, and EOS adopt proof of stake consensus. Lastly, proof of authority. A modified form of proof of stake. Here, only approved parties selected based on their reputation can become validators. Let's revisit the treasure chest scenario. The group of treasure hunters form a union and pool their treasures. Based on their level of trustworthiness, a select few are appointed by the group to ensure the validity of the chest's content. IBM's Hybrid Fabric and Ethereum's Core testnet are some examples of blockchain systems that use proof of authority. While traditional blockchain companies exist on a single consensus mechanism, some innovative ones are adopting multiple consensus protocols. Take Go-eth Foundation, for example, who is building a unique blockchain to store data collected on its tuition companion chatbot app, applying both proof of authority and proof of work protocols. Data such as students' academic, extracurricular, and personality profiling records are stored on the blockchain and potentially validated by a proof of authority framework powered by Hybrid Fabric. Validators in this instance are reputable educational institutions or even national registrars and respective ministries of education. This helps ensure that all student data is trustworthy. But who will work for free? Proof of work consensus thus comes into play to reward validators who have performed the work. With Hybrid Fabric, each student record is secured with a private hash key owned by the student. The data can only be accessed when the students provide the unique key. This means student privacy is preserved and controlled by the student themselves. For example, when students apply to university via Go-eth's platform, they will provide the unique key of their records to the university. With that, the university will be able to access their latest academic records. Students will also be able to see if their records have been unlocked or at least considered for application. This boosts efficiency and transparency compared to traditional methods. By marrying the proof of work and proof of authority models, Go-eth Foundation's blockchain solution ensures privacy on students' data while incentivizing both educational institutions and students when they contribute to Go-eth's platform. With blockchains gaining popularity, it's only a matter of time before we see even more unique hybrid systems created.
Gasper. Last edit at Wacaro, August 15, 2022. Gasper is a combination of Casper the friendly finality gadget, Casper FFG, and the LMD Ghost fork choice algorithm. Together these components form the consensus mechanism securing proof of stake Ethereum. Casper is the mechanism that upgrades certain blocks to finalized so that new entrants into the network can be confident that they are syncing the canonical chain. The fork choice algorithm uses accumulated votes to ensure that nodes can easily select the correct one when forks arise in the blockchain. Note that the original definition of Casper FFG was updated slightly for inclusion in Gasper. On this page we consider the updated version. Prerequisites. To understand this material, it is necessary to read the introductory page on proof of stake. The role of Gasper. Proof of stake, POS. Last edit at Corwin Times, January 12, 2023. Proof of stake, POS, underlies Ethereum's consensus mechanism. Proof of stake, POS. What is proof of stake, POS? Proof of stake underlies certain consensus mechanisms used by blockchains to achieve distributed consensus. In proof of work, miners prove they have capital at risk by expending energy. Ethereum uses proof of stake, where validators explicitly stake capital in the form of ETH into a smart contract on Ethereum. This staked ETH then acts as collateral that can be destroyed if the validator behaves dishonestly or lazily. The validator is then responsible for checking that new blocks propagated over the network are valid and occasionally creating and propagating new blocks themselves. Proof of stake comes with a number of improvements to the now deprecated proof of work system. Better energy efficiency, there is no need to use lots of energy on proof of work computations. Lower barriers to entry, reduced hardware requirements, there is no need for elite hardware to stand a chance of creating new blocks. Reduced centralization risk, proof of stake should lead to more nodes securing the network. Because of the low energy requirement, less ETH issuance is required to incentivize participation. Economic penalties for misbehavior make 51% style attacks exponentially more costly for an attacker compared to proof of work. The community can resort to social recovery of an honest chain if a 51% attack were to overcome the crypto economic defenses. Validators. To participate as a validator, a user must deposit 32 ETH into the deposit contract and run 3 separate pieces of software, an execution client, a consensus client, and a validator. On depositing their ETH, the user joins an activation queue that limits the rate of new validators joining the network. Once activated, validators receive new blocks from peers on the Ethereum network. The transactions delivered in the block are re-executed, and the block signature is checked to ensure the block is valid. The validator then sends a vote, called an attestation, in favor of that block across the network. Whereas under proof of work, the timing of blocks is determined by the mining difficulty, in proof of stake, the tempo is fixed. Time in proof of stake Ethereum is divided into slots, 12 seconds, and epochs, 32 slots. One validator is randomly selected to be a block proposer in every slot. This validator is responsible for creating a new block and sending it out to other nodes on the network. Also in every slot, a committee of validators is randomly chosen, whose votes are used to determine the validity of the block being proposed. How a transaction gets executed in Ethereum POS. The following provides an end-to-end explanation of how a transaction gets executed in Ethereum proof of stake. A user creates and signs a transaction with their private key. This is usually handled by a wallet or a library such as Ether.js, Web3.js, Web3.py etc. But under the hood the user is making a request to a node using the Ethereum JSON RPC API. The user defines the amount of gas that they are prepared to pay as a tip to a validator to encourage them to include the transaction in a block. The tips get paid to the validator while the base fee gets burned. The transaction is submitted to an Ethereum execution client which verifies its validity. This means ensuring that the sender has enough ETH to fulfill the transaction and they have signed it with the correct key. If the transaction is valid, the execution client adds it to its local mempool, list of pending transactions, and also broadcasts it to other nodes over the execution layer gossip network. When other nodes hear about the transaction they add it to their local mempool too. Advanced users might refrain from broadcasting their transaction and instead forward it to specialized blocks. The transaction is submitted to an Ethereum execution client which verifies its validity. This means ensuring that the sender has enough ETH to fulfill the transaction and they have signed it with the correct key. If the transaction is valid, the execution client adds it to its local mempool, list of pending transactions, and also broadcasts it to other nodes over the execution layer gossip network. When other nodes hear about the transaction they add it to their local mempool too. Advanced users might refrain from broadcasting their transaction and instead forward it to specialized block builders such as Flashbot's auction. This allows them to organize the transactions in upcoming blocks for maximum profit, MEV. One of the nodes on the network is the block proposer for the current slot, having previously been selected pseudo-randomly using Randeo. This node is responsible for building and broadcasting the next block to be added to the Ethereum blockchain and updating the global state. The node is made up of 3 parts, an execution client, a consensus client and a validator client. The execution client bundles transactions from the local mempool into an execution payload and executes them locally to generate a state change. This information is passed to the consensus client where the execution payload is wrapped as part of a beacon block that also contains information about rewards, penalties, slashings, attestations etc. that enable the network to agree on the sequence of blocks at the head of the chain. The communication between the execution and consensus clients is described in more detail in connecting the consensus and execution clients. Other nodes receive the new beacon block on the consensus layer gossip network. They pass it to their execution client where the transactions are re-executed locally to ensure the proposed state change is valid. The validator client then attests that the block is valid and is the logical next block in their view of the chain, meaning it builds on the chain with the greatest weight of attestations as defined in the fork choice rules. The block is added to the local database in each node that attests to it. The transaction can be considered finalized, i.e., that it cannot be reverted, if it has become part of a chain with a supermajority link between 2 checkpoints. Checkpoints occur at the start of each epoch and to have a supermajority link they must both be attested to by 66% of the total staked ETH on the network. More detail on finality can be found below. Finality. A transaction has finality in distributed networks when it's part of a block that can't change without a significant amount of ETH getting burned. On proof-of-stake Ethereum, this is managed using checkpoint blocks. The first block in each epoch is a checkpoint. Validators vote for pairs of checkpoints that it considers to be valid. If a pair of checkpoints attracts votes representing at least 2/3 of the total staked ETH, the checkpoints are upgraded. The more recent of the two, target, becomes justified. The earlier of the two is already justified because it was the target in the previous epoch. Now it is upgraded to finalized. To revert a finalized block, an attacker would commit to losing at least 1/3 of the total supply of staked ETH. The exact reason for this is explained in this Ethereum Foundation blog post. Since finality requires a 2/3 majority, an attacker could prevent the network from reaching finality by voting with 1/3 of the total stake. There is a mechanism to defend against this, the inactivity leak. This activates whenever the chain fails to finalize for more than 4 epochs. The inactivity leak bleeds away the staked ETH from validators voting against the majority, allowing the majority to regain a 2/3 majority and finalize the chain. Crypto economic security. Running a validator is a commitment. The validator is expected to maintain sufficient hardware and connectivity to participate in block validation and proposal. In return, the validator is paid in ETH, their staked balance increases. On the other hand, participating as a validator also opens new avenues for users to attack the network for personal gain or sabotage. To prevent this, validators miss out on ETH rewards if they fail to participate when called upon, and their existing stake can be destroyed if they behave dishonestly. There are 2 primary behaviors that can be considered dishonest: proposing multiple blocks in a single slot, equivocating, and submitting contradictory attestations. The amount of ETH/ depends on how many validators are also being slashed at around the same time. This is known as the correlation penalty, and it can be minor, 1% stake for a single validator slashed on their own, or can result in 100% of the validator's stake getting destroyed, mass slashing event. It is imposed halfway through a forced exit period that begins with an immediate penalty, up to 0.5 ETH, on day 1, the correlation penalty on day 18, and finally, ejection from the network on day 36. They receive minor attestation penalties every day because they are present on the network but not submitting votes. This all means a coordinated attack would be very costly for the attacker. Fork choice. When the network performs optimally and honestly, there is only ever one new block at the head of the chain, and all validators attest to it. However, it is possible for validators to have different views of the head of the chain due to network latency or because a block proposer has equivocated. Therefore, consensus clients require an algorithm to decide which one to favor. The algorithm used in proof-of-stake Ethereum is called LMD Go-eth, and it works by identifying the fork that has the greatest weight of attestations in its history. Proof-of-stake insecurity. The threat of a 51% attack. Fork choice. When the network performs optimally and honestly, there is only ever one new block at the head of the chain, and all validators attest to it. However, it is possible for validators to have different views of the head of the chain due to network latency or because a block proposer has equivocated. Therefore, consensus clients require an algorithm to decide which one to favor. The algorithm used in proof-of-stake Ethereum is called LMD Go-eth, and it works by identifying the fork that has the greatest weight of attestations in its history. Proof-of-stake insecurity. The threat of a 51% attack still exists on proof-of-stake as it does on proof-of-work, but it's even riskier for the attackers. An attacker would need 51% of the staked ETH. They could then use their own attestations to ensure their preferred fork was the one with the most accumulated attestations. The weight of accumulated attestations is what consensus clients use to determine the correct chain, so this attacker would be able to make their fork the canonical one. However, a strength of proof-of-stake over proof-of-work is that the community has flexibility in mounting a counter-attack. For example, the honest validators could decide to keep building on the minority chain and ignore the attacker's fork while encouraging apps, exchanges, and pools to do the same. They could also decide to forcibly remove the attacker from the network and destroy their staked ETH. These are strong economic defenses against a 51% attack. 51% attacks are just one flavor of malicious activity. Bad actors could attempt long-range attacks, although the finality gadget neutralizes this attack vector. Short-range reorgs, although proposer boosting and attestation deadlines mitigate this. Bouncing and balancing attacks, also mitigated by proposer boosting. And these attacks have anyway only been demonstrated under idealized network conditions, or avalanche attacks, neutralized by the fork choice algorithm's rule of only considering the latest message. Overall, proof-of-stake, as it is implemented on Ethereum, has been demonstrated to be more economically secure than proof-of-work. Pros and cons. Pros-cons. Staking makes it easier for individuals to participate in securing the network, promoting decentralization. Validator node can be run on a normal laptop. Staking pools allow users to stake without having 32 ETH. Proof-of-stake is younger and less battle-tested compared to proof-of-work. Staking is more decentralized. Economies of scale do not apply in the same way that they do for POW mining. Proof-of-stake is more complex to implement than proof-of-work. Proof-of-stake offers greater crypto-economic security than. Proof-of-work users need to run 3 pieces of software to participate in Ethereum's proof-of-stake. Less issuance of new ETH is required to incentivize network participants. More of a visual learner? Further reading.
What is proof of stake? The proof of stake consensus algorithm was introduced back in 2011 on the Bitcoin Talk forum to solve the problems of the current most popular algorithm in use, proof of work. While they both share the same goal of reaching consensus in the blockchain, the process to reach the goal is quite different. How does it work? The proof of stake algorithm uses a pseudo-random election process to select a node to be the validator of the next block, based on a combination of factors that could include the staking age, randomization, and the node's wealth. It's good to note that in proof of stake systems, blocks are said to be forged rather than mined. Cryptocurrencies using proof of stake often start by selling pre-mined coins, or they launch with a proof of work algorithm and then later switch over to proof of stake. Where in proof of work based systems, more and more cryptocurrency is created as rewards for the miners. The proof of stake system usually uses transaction fees as a reward. Users who want to participate in the forging process are required to lock a certain amount of coins into the network as their stake. The size of the stake determines the chances for a node to be selected as the next validator to forge the next block. The bigger the stake, the bigger the chances. In order for the process not to favor only the wealthiest nodes in the network, more unique methods are added into the selection process. The 2 most commonly used methods are randomized block selection and coin age selection. In the randomized block selection method, the validators are selected by looking for nodes with a combination of the lowest hash value and the highest stake. Since the size of the stakes are public, the next forger can usually be predicted by other nodes. The coin age selection method chooses nodes based on how long their tokens have been staked for. Coin age is calculated by multiplying the number of days the coins have been held as stake by the number of coins that are staked. Once a node has forged a block, their coin age is reset to 0, and they must wait a certain certain period of time to be able to forge another block. This prevents large stake nodes from dominating the blockchain. Each cryptocurrency using proof of stake algorithm has their own set of rules and methods combined for what they think is the best possible combination for them and their users. When a node gets chosen to forge the next block, it will check if the transactions in the block are valid, signs the block, and adds it to the blockchain. As a reward, the node receives the transaction fees that are associated with the transactions in the block. If a node wants to stop being a forger, its stake along with the earned rewards will be released after a certain period of time, giving the network time to verify that there are no fraudulent blocks added to the blockchain by the node. Security. The stake works as a financial motivator for the forger not to validate or create fraudulent transactions. If the network detects a fraudulent transaction, the forger node will lose a part of its stake and its right to participate as a forger in the future. So long as the stake is higher than the reward, the validator would lose more coins than it would gain in case of attempting fraud. In order to effectively control the network and approve fraudulent transactions, a node would have to own a majority stake in the network, also known as the 51% attack. Depending on the value of a cryptocurrency, this would be very impractical, as in order to gain control of the network, you would need to acquire 51% of the circulating supply. The main advantages of the proof of stake algorithm are energy efficiency and security. A greater number of users are encouraged to run nodes since it's easy and affordable. This, along with the randomization process, also makes the network more decentralized, since mining pools are no longer needed to mine the blocks. And since there is less of a need to release many new coins for a reward, this helps the price of a particular coin to stay more stable. It's good to remember that the cryptocurrency industry is rapidly changing and evolving, and there are also several other algorithms and methods being developed and experimented with. Stay tuned for more content, and don't forget to check out our other videos at Binance Academy.
Crypto-economic security. Running a validator is a commitment. The validator is expected to maintain sufficient hardware and connectivity to participate in block validation and proposal. In return, the validator is paid in ETH, their staked balance increases. On the other hand, participating as a validator also opens new avenues for users to attack the network for personal gain or sabotage. To prevent this, validators miss out on ETH rewards if they fail to participate when called upon, and their existing stake can be destroyed if they behave dishonestly. There are two primary behaviors that can be considered dishonest: proposing multiple blocks in a single slot, equivocating, and submitting contradictory attestations. The amount of ETH/ depends on how many validators are also being slashed at around the same time. This is known as the correlation penalty, and it can be minor, 1% stake for a single validator slashed on their own, or can result in 100% of the validator's stake getting destroyed, mass slashing event. It is imposed halfway through a forced exit period that begins with an immediate penalty, up to 0.5 ETH, on day 1, the correlation penalty on day 18, and finally, ejection from the network on day 36. They receive minor attestation penalties every day because they are present on the network but not submitting votes. This all means a coordinated attack would be very costly for the attacker. Fork choice. When the network performs optimally and honestly, there is only ever one new block at the head of the chain, and all validators attest to it. However, it is possible for validators to have different views of the head of the chain due to network latency or because a block proposer has equivocated. Therefore, consensus clients require an algorithm to decide which one to favor. The algorithm used in proof-of-stake Ethereum is called LMD Ghost, and it works by identifying the fork that has the greatest weight of attestations in its history. Proof-of-stake insecurity. The threat of a 51% attack still, a user creates and signs a transaction with their private key. This is usually handled by a wallet or a library. If the transaction is valid, the execution client adds it to its local mempool, list of pending transactions, and also broadcasts it to other nodes over the execution layer gossip network. When other nodes hear about the transaction, they add it to their local mempool too. Advanced users might refrain from broadcasting their transaction and instead forward it to specialized block builders such as Flashbot's auction. This allows them to organize the transactions in upcoming blocks for maximum profit, MEV. One of the nodes on the network is the block proposer for the current slot, having previously been selected pseudo-randomly using Randao. This node is responsible for building and broadcasting the next block to be added to the Ethereum blockchain and updating the global state. The node is made up of 3 parts: an execution client, a consensus client, and a validator client. The execution client bundles transactions from the local mempool into an execution payload and executes them locally to generate a state change. This information is passed to the consensus client, where the execution payload is wrapped as part of a beacon block that also contains information about rewards, penalties, slashings, attestations, etc. that enable the network to agree on the sequence of blocks at the head of the chain. The communication between the execution and consensus clients is described in more detail in connecting the consensus and execution clients. Other nodes receive the new beacon block on the consensus layer gossip network. They pass it to their execution client, where the transactions are re-executed locally to ensure the proposed state change is valid. Other nodes receive the new beacon block on the consensus layer gossip network. They pass it to their execution client, where the transactions are re-executed locally to ensure the proposed state change is valid. The validator client then attests that the block is valid and is the logical next block in their view of the chain, meaning it builds on the chain with the greatest weight of attestations as defined in the fork choice rules. The block is added to the local database. The block is added to the local database in each node that attests to it. The transaction can be considered finalized, i.e., that it cannot be reverted, if it has become part of a chain with a supermajority link between 2 checkpoints. Checkpoints occur at the start of each epoch, and to have a supermajority link they must both be attested to by 66% of the total staked ETH on the network. More detail on finality can be found below. Finality. A transaction has finality in distributed networks when it's part of a block that can't change without a significant amount of ETH getting burned. On proof-of-stake Ethereum, this is managed using checkpoint blocks. The first block in each epoch is a checkpoint. Validators vote for pairs of checkpoints that it considers to be valid. If a pair of checkpoints attracts votes representing at least 2/3 of the total staked ETH, the checkpoints are upgraded. The more recent of the two, target, becomes justified. The earlier of the two is already justified because it was the target in the previous epoch. Now it is upgraded to finalized. To revert a finalized block, an attacker would commit to losing at least 1/3 of the total supply of staked ETH. The exact reason for this is explained in this Ethereum Foundation blog post. Since finality requires a 2/3 majority, an attacker could prevent the network from reaching finality by voting with 1/3 of the total stake. There is a mechanism to defend against this, the inactivity leak. This activates whenever the chain fails to finalize for more than 4 epochs. The inactivity leak bleeds away the staked ETH from validators voting against the majority, allowing the majority to regain a 2/3 majority and finalize the chain. Crypto economic security. Running a validator is a commitment. The validator is expected to maintain sufficient hardware and connectivity to participate in block validation and proposal. In return, the validator is paid in ETH, their staked balance increases. On the other hand, participating as a validator also opens new avenues for users to attack the network for personal gain or sabotage. To prevent this, validators miss out on ETH rewards if they fail to participate when called upon, and their existing stake can be destroyed if they behave dishonestly. There are two primary behaviors that can be considered dishonest: proposing multiple blocks in a single slot, equivocating, and submitting contradictory attestations. The amount of ETH/ depends on how many validators are also being Gasper. Last edit at Wackero. Gasper is a combination of Casper the friendly finality gadget, Casper FFG, and the LMD Ghost fork choice algorithm. Together these components form the consensus mechanism securing proof-of-stake Ethereum. Casper is the mechanism that upgrades certain blocks to finalized so that new entrants into the network can be confident that they are syncing the canonical chain. The fork choice algorithm uses accumulated votes to ensure that nodes can easily select the correct one when forks arise in the blockchain. Note that the original definition of Casper FFG was updated slightly for inclusion in Gasper. On this page we consider the updated version. Prerequisites. To understand this material it is necessary to read the introductory page on proof of stake.
So this is the key here, I think, for what I'm looking for that I was talking about. So the most important part is understanding how Gasper works and how this fork choice algorithm works. Because it's pretty much the difference between, one of the fundamental differences between proof of stake and proof of work. That when uncle blocks arise on proof of stake, it's going to be determined by this fork choice algorithm, which chain is the correct one, and then on proof of work is the longest chain, which means that is the chain that is the most difficulty, that has the highest difficulty because it builds on top of the whole history of the blockchains. So it seems that it's going to be easier to understand on this one because it's more clear that each node is going to pass the transactions. And then the whole part of centralization happens before with the block building, where each node, each specific mempool, or each node can organize the transactions before sending to its mempool, and then send the transactions to other nodes after that. And the thing that I'm not sure is, yeah, I think after I studied this on proof of stake, the algorithm is going to be easier to understand in proof of work as well, how it worked. Because if you have several different uncle blocks in proof of work, it's still not clear to me how you would decide, how each local node would decide to change its history. Yeah, it depends on how different it's going to be on average on different pockets of the network, the amount of transactions that they are receiving. Yeah, I guess that if nodes are receiving less transactions, then the tendency is going to be for them to not incorporate the blocks into the history. At least that's what it seems like. But because the computational rate is not that much different on all of the different RPC providers, then it ends up working out because then most of the nodes are going to be roughly in sync because they are updating the same transactions. But if you had a situation where there's too big of a gap on the computation, then what happens is that one pocket of the network is gonna start building blocks that are not in the same order as the other pocket because the flow of information from both of them is different because one is receiving a lot more information, which is a lot more transactions than the other one. And what that makes it is so that that pocket of the network is gonna put a bunch of blocks faster than the other ones. So the other ones are eventually going to discard their local history and adopt the ones that are bigger. And that's the whole thing about decentralization that was happening with proof of work, because it generates this cascading effect where you have specialized miners that get more and more resources, and then it creates a Pareto distribution. And then you have on top of that the MEV, and the MEV creates this disproportion because there's also the same effect of centralization where you have people that start specializing in building the blocks and then validating the transactions off chain, and then only after that they send the transactions to their mempool and then propagate those transactions in the network. But because they have a lot more flow of transactions, they are going to put blocks faster on leverage than all the other nodes, I think. So the history that ends up being true is the history that I think it doesn't matter that much because obviously the transactions are going to be valid. So, but it does matter because of the order. The order matters. So the speed matters, I think. But I remember when I was studying with ChatGPT, asking questions, like the way that he responded, it seemed like it doesn't, like they're not gonna be. It doesn't matter if there is one of the nodes that is a lot faster than the other ones. That's what ChatGPT was saying. But in my mind, it seems like it does matter because the fastest one is gonna determine. And this is the thing, like, because it is confusing because how is it possible for you to validate the transactions? I guess you can validate the transactions off, but then the blocks is the difference. Because in order to reach the consensus, you depend on other nodes. So the order of blocks is always in sync, so it doesn't matter which one is fastest. Because the only way to validate the blocks is through the. That's what's creating confusion in me, I think. Because to validate the blocks, then you need to propagate the transactions on the network. But to validate the transactions, you don't need to propagate them. But either way, it's kind of confusing because let's say you have one node that is receiving 200,000 transactions, let's say. And 200,000 transactions is equivalent to 5 blocks. And then you have another node that is receiving 40,000 transactions, which is equivalent to 1 block. That means that the node that receives 200,000 transactions is going to create 5 blocks in the time that the other node creates 1 block. And if they both have their local history, it means that one node's local history is going to be 5 blocks ahead than the other node. So it means that the uncle blocks of that node are going to always be bigger than the other one. That's like what doesn't make sense to me, because then the discrepancies on the difference of the computation on different pockets of the network determine which chain is more likely to be the main chain, because the longest one wins. Like that has to be the case, I think. But the only thing that makes it so that it doesn't become centralized is because it's very difficult to have that big of a gap in computation. But then the problem is if you have MEV, it starts to get centralized because then everyone is incentivized to only use a couple of RPC providers, and then those RPC providers have their node, and their node is going to be at an advantage because the flow of information is always going to be higher for them. And the computation as well, because they can use that power, that asymmetry, to create more and more, which creates the exponential distribution. which means that they're always going to be putting blocks in the network faster than the other nodes, which means that it's more likely for the other nodes to have to discard their history and adopt the. But the thing that it doesn't make sense as well is because, like, at some point there needs to be transactions that are mixed from both nodes, let's say. So if you have something like in this I'm talking on proof of work, obviously. Let's say you have some node that received transactions from flashbots, and the transactions they received was already the block finalized. Then how would that node incorporate other transactions that are also happening in the network? If it is only putting transactions that is receiving from its RPC provider. I guess like it would receive other transactions as well through the network, but it would always be less than. Like that's the thing that it doesn't make any sense. Is like what are the breaking points here? How do you decide when something is considered to be a block and when it isn't? And I remember reading that it was based on gas, the size of the block, and the way they did it. The reason why they did it like this is so that it changes with the congestion of the network, and also so you don't have the infinite loop problem where it halts the execution because it's single threaded. So if you want more computation, then you have to pay more gas, which stops people from breaking the whole chain. But it doesn't make any sense to me, these parts of the uncle blocks. Like, how do you determine when it is a block and when it isn't? And then how do you merge different transactions from different nodes? Taking into consideration that a lot of the computation is going to be done off-chain because it's specialized. It doesn't make any sense. I'm contemplating whether or not to, because I want to understand, but problem is now it's proof of stake, so it might be a waste of time to study that. And it's something that I think I will only be able to answer by studying the source code because I haven't seen it anywhere. Explain it like this. Now, obviously the documentation is very good, but for these nuances here, I think is not enough. Unless I'm missing some parts of the documentation, that's possible as well. About the gas here. Let me read this one. But I think those are the main things that I'm going to focus now is one, the algorithm, the fork choice, fork algorithm, however you say that. And also try to understand this, what determines when a node should pass transactions through other nodes' mempools and how they are synchronized. How are they synchronized?
Last edit at Wacker. Last edit at Wacker, September 29th, 2022. Blocks are batches of transactions with the hash of the previous block in the chain. This links blocks together, in a chain, because hashes are cryptographically derived from the block data. This prevents fraud, because one change in any block in history would invalidate all the following blocks as all subsequent hashes would change and everyone running the blockchain would notice. Prerequisites. Blocks are a very beginner-friendly topic. But to help you better understand this page, we recommend you first read accounts, transactions, and our introduction to Ethereum. Why blocks? To ensure that all participants on the Ethereum network maintain a synchronized state and agree on the precise history of transactions, we batch transactions into blocks. This means dozens, or hundreds, of transactions are committed, agreed on, and synchronized all at once. Diagram adapted from Ethereum EVM illustrated. By spacing out commits, we give all network participants enough time to come to consensus. Even though transaction requests occur dozens of times per second, blocks are only created and committed on Ethereum once every 12 seconds. How blocks work. To preserve the transaction history, blocks are strictly ordered. Every new block created contains a reference to its parent block, and transactions within blocks are strictly ordered as well. Except in rare cases, at any given time, all participants on the network are in agreement on the exact number and history of blocks, and are working to batch the current live transaction requests into the next block. Once a block is put together by some validator on the network, it is propagated to the rest of the network. All nodes add this block to the end of their blockchain, and a new validator is selected to create the next block. The exact block assembly process and commitment/consensus process is currently specified by Ethereum's proof-of-stake protocol. Proof-of-stake protocol. Proof-of-stake means the following. Validating nodes have to stake 32 ETH into a deposit contract as collateral against bad behavior. This helps protect the network because provably dishonest activity leads to some or all of that stake being destroyed. In every slot, spaced 12 seconds apart, a validator is randomly selected to be the block proposer. They bundle transactions together, execute them and determine a new state. They wrap this information into a block and pass it around to other validators. Other validators who hear about a new block re-execute the transactions to ensure they agree with the proposed change to the global state. Assuming the block is valid, they add it to their own database. If a validator hears about two conflicting blocks for the same slot, they use their fork choice algorithm to pick the one supported by the most staked ETH. More on proof of stake. What's in a block? There is a lot of information contained within a block. At the highest level, a block contains the following fields. Field description slot the block belongs top proposer indexed ID of the validator proposing the block time. Block time refers to the time separating blocks. In Ethereum, time is divided up into 12-second units called slots. In each slot, a single validator is selected to propose a block. Assuming all validators are online and fully functional, there will be a block in every slot, meaning the block time is 12s. However, occasionally validators might be offline when called to propose a block, meaning slots can sometimes go empty. This is different to proof-of-work-based systems where block times are probabilistic and tuned by the mining difficulty. Block size. A final important note is that blocks themselves are bounded in size. Each block has a target size of 15 million gas, but the size of blocks will increase or decrease in accordance with network demands, up until the block limit of 30 million gas, 2x target block size. The total amount of gas expended by all transactions in the block must be less than the block gas limit. This is important because it ensures that blocks can't be arbitrarily large. If blocks could be arbitrarily large, then less performant full nodes would gradually stop being able to keep up with the network due to space and speed requirements. The larger the block, the greater the computing power required to process them in time for the next slot. This is a centralizing force, which is resisted by capping block sizes. Further reading. Know of a community resource that helped you? Proof-of-work mining with Ethish. Note. Proof-of-work mining is no longer used to secure Ethereum mainnet. The information below is included because the Ethish code is still part of Go-eth and it could be used to create a private proof-of-work network or testnet. Blockchains grow when individual nodes create valid blocks and distribute them to their peers who check the blocks and add them to their own local databases. Nodes that add blocks are rewarded with Ether payouts. On Ethereum mainnet, the proof-of-stake consensus engine randomly selects a node to produce each block. Ethereum wasn't always secured this way. Originally, a proof-of-work-based consensus mechanism was used instead. Under proof-of-work, block producers are not selected randomly in each slot. Instead, they compete for the right to add a block. The node that is fastest to compute a certain value that can only be found using brute force calculations is the one that gets to add a block. Only if a node can demonstrate that they have calculated this value, and therefore expended energy, will their block be accepted by other nodes. This process of creating blocks and securing them using proof of work is known as mining. Much more information about mining, including details about the specific algorithm, Ethish, used by Ethereum nodes is available on ethereum.org. CPU vs GPU. Ethereum mining used an algorithm called Ethish. Go-eth includes a CPU miner which runs Ethish within the Go-eth process. Everything required to mine on a CPU is bundled with Go-eth. However, to mine using GPUs an additional piece of third-party software is required. The most commonly used GPU mining software is Ethminer. Regardless of the mining method, the blockchain must be fully synced before mining is started, otherwise the miner will build on an outdated sidechain, meaning block rewards will not be recognized by the main network. GPU mining. Installing Ethminer. The Ethminer software can be installed from a downloaded binary or built from source. The relevant downloads and installation instructions are available from the Ethminer GitHub. Standalone executables are available for Linux, Mac OS, and Windows. Using Ethminer with Go-eth. An account to receive block rewards must first be defined. The address of the account is all that is required to start mining. The mining rewards will be credited to that address. This can be an existing address or one that is newly created by Go-eth. More detailed instructions on creating and importing accounts are available on the account management page. The account address can be provided to mining.etherbase when Go-eth is started. This instructs Go-eth to direct any block rewards to this address. Once started, Go-eth will sync the blockchain. If Go-eth has not connected to this network before, or if the data directory has been deleted, this can take several days. Also, enable HTTP traffic with the HTTP command. The progress of the blockchain syncing can be monitored by attaching a JavaScript console in another terminal. More detailed information about the console can be found on the JavaScript console page. Then in the console, to check if the sync is progressing correctly, the output. Once the blockchain is synced, mining can begin. In order to begin mining, Ethminer must be run and connected to Go-eth in a new terminal. OpenCL can be used for a wide range of GPUs. CUDA can be used specifically for NVIDIA GPUs. Hashtag OpenCL Ethminer communicates with Go-eth on port 8545, Go-eth's default RPC port, but this can be changed by providing a custom port to the http.port command. The corresponding port must also be configured in Ethminer by providing phttp://. This is necessary when multiple instances of Go-eth/Ethminer will coexist on the same machine. If using OpenCL and the default for Ethminer does not work, specifying the device using the OpenCLdeviceX command is a common fix. X is an integer 1, 2, 3, etc. The Ethminer benchmark command should display something that looks like benchmarking on platform. Note that the Go-eth command miner.hashrate only works for CPU mining. It always reports 0 for GPU mining. To check the GPU mining hash rate, check the logs Ethminer displays to its terminal. More verbose logs can be configured using v in a value between 0 to 9. The Ethish algorithm is memory hard and requires a large dataset to be loaded into memory. Each GPU requires 4 to 5 GB of RAM. The error message error GPU mining. GPU memory fragmentation indicates that there is insufficient memory available. CPU mining with Go-eth. When Go-eth is started, it is not mining by default. Unless it is specifically instructed to mine, it acts only as a node, not a miner. Go-eth starts as a CPU miner if the mine flag is provided. The miner.threads parameter can be used to set the number of parallel mining threads, defaulting to the total number of processor cores. Go-eth mine miner.threads equals 4. CPU mining can also be started and stopped at runtime using the console. The command miner.start takes an optional parameter for the number of miner threads. Miner.start, 8, true. Note that mining only makes sense if you are in sync with the network, since you mine on top of the consensus block. Therefore the blockchain downloader/synchronizer will delay mining until syncing is complete, and after that mining automatically starts unless you cancel with miner.stop. Like with GPU mining, an Etherbase account must be set. This defaults to the primary account in the key store but can be set to an alternative address using the miner.etherbase command. If there is no account available, an account will be created and automatically configured to be the Coinbase. The JavaScript console can be used to reset the Etherbase account at runtime. Miner.setEtherbase. Note that your Etherbase does not need to be an address of a local account, it just has to be set to an existing one. There is an option to add extra data, 32 bytes only, to the mined blocks. By convention this is interpreted as a Unicode string, so it can be used to add a short vanity tag using mine. The console can also be used to check the current hash rate in units h/s, hash operations per second. eth.hashrate 700. After some blocks have been mined, the Etherbase account balance with be greater than 0. Assuming the Etherbase is a local account, it is also possible to check which blocks were mined by a particular miner address, using the following code snippet in the JavaScript console. The Etherbase balance will fluctuate if a mined block is reorged out of the canonical chain. This means that when the local Go-eth node includes the mined block in its own local blockchain, the account balance appears higher because the block rewards are applied. When the node switches to another version of the chain due to information received from peers, that block may not be included and the block rewards are not applied. The logs show locally mined blocks can Proof of work, POW. Last edit at Wakaro, the Ethereum network began by using a consensus mechanism that involved proof of work, POW. This allowed the nodes of the Ethereum network to agree on the state of all information recorded on the Ethereum blockchain and prevented certain kinds of economic attacks. However, Ethereum switched off proof of work in 2022 and started using proof of stake instead. Proof of work has now been deprecated. Ethereum no longer uses proof of work as part of its consensus mechanism. Instead, it uses proof of stake. Read more on proof of stake and staking. Prerequisites. What is proof of work, POW? Nakamoto consensus, which utilizes proof of work, is the mechanism that once allowed the decentralized Ethereum network to come to consensus, i.e. all nodes agree, on things like account balances and the order of transactions. This prevented users from double spending their coins and ensured that the Ethereum chain was tremendously difficult to attack or manipulate. These security properties now come from proof of stake instead using the consensus mechanism known as Gasper. Proof of work in mining. Proof of work is the underlying algorithm that sets the difficulty and rules for the work miners do on proof of work blockchains. Mining is the work itself. It's the act of adding valid blocks to the chain. This is important because the chain's length helps the network follow the correct fork of the blockchain. The more work done, how did Ethereum's proof of work work? Ethereum transactions are processed into blocks. In the now deprecated proof of work Ethereum, each block contained this block data was directly related to proof of work. The work in proof of work, the proof of work protocol, Ethish, required miners to go through an intense race of trial and error to find the nonce for a block. Only blocks with a valid nonce could be added to the chain. When racing to create a block, a miner repeatedly put a dataset that could only be obtained by downloading and running the full chain, as a miner does, through a mathematical function. The dataset was used to generate a mix hash below a target that is dictated by the block difficulty. The best way to do this is through trial and error. The difficulty determined the target for the hash. The lower the target, the smaller the set of valid hashes. Once generated, this was incredibly easy for other miners and clients to verify. Even if one transaction were to change, the hash would be completely different, signaling fraud. Hashing makes fraud easy to spot. But proof of work as a process was also a big deterrent to attacking the chain. Proof of work insecurity. Miners were incentivized to do this work on the main Ethereum chain. There was little incentive for a subset of miners to start their own chain. It undermines the system. Blockchains rely on having a single state as a source of truth. The objective of proof of work was to extend the chain. The longest chain was most believable as the valid one because it had the most computational work done to generate it. Within Ethereum's POW system, it was nearly impossible to create new blocks that erase transactions, create fake ones, or maintain a second chain. That's because a malicious miner would have needed to always solve the block nonce faster than everyone else. To consistently create malicious yet valid blocks, a malicious miner would have needed over 51% of the network mining power to beat everyone else. That amount of work requires a lot of expensive computing power, and the energy spent might even have outweighed the gains made in an attack. Proof of work economics. Proof of work was also responsible for issuing new currency into the system and incentivizing miners to do the work. Since the Constantinople upgrade, miners who successfully create a block were rewarded with 2 freshly minted ETH and part of the transaction fees. Omer blocks also compensated 1.75 ETH. Omer blocks were valid blocks created by a miner practically at the same time as another miner created the canonical block, which was ultimately determined by which chain was built on top of first. Omer blocks usually happened due to network latency. Finality. A transaction has finality on Ethereum when it's part of a block that can't change. Because miners worked in a decentralized way, 2 valid blocks could be mined at the same time. This creates a temporary fork. Eventually, one of these chains became the accepted chain after subsequent blocks were mined and added to it, making it longer. To complicate things further, transactions rejected on the temporary fork may not have been included in the accepted chain. This means it could get reversed. So finality refers to the time you should wait before considering a transaction irreversible. Under the previous proof of work Ethereum, the more blocks were mined on top of a specific block N, the higher confidence that the transactions in N were successful and would not be reverted. Now, with proof of stake, finalization is an explicit, rather than probabilistic, property of a block. Proof of work energy usage. A major criticism of proof of work is the amount of energy output required to keep the network safe. To maintain security and decentralization, Ethereum on proof of work consumed large amounts of energy. Shortly before switching to proof of stake, Ethereum miners were collectively compared to proof of stake. At a high level, proof of stake.
What is proof of work? Originally dated back in 1993, the proof of work concept was developed to prevent denial of service attacks and other service abuse such as spam on a network by requiring some work from the service user, usually meaning processing time by a computer. In 2009, Bitcoin introduced an innovative way of using proof of work as a consensus algorithm that is used to validate transactions and broadcast new blocks to the blockchain. It has then spread to become a widely used consensus algorithm in many cryptocurrencies. How does it work? In short, miners on a network will compete against each other in solving complex computational puzzles. These puzzles are difficult to solve, but very easy to verify the correct solution. Once a miner has found a solution to a puzzle, they will be able to broadcast the block to the network, where all the other miners will then verify that the solution is correct. Let's take an example. Bitcoin is a blockchain-based system that is maintained by the collective work of decentralized nodes. Some of these nodes are known as miners and are responsible for adding new blocks into the blockchain. In order to do so, miners need to try and guess a pseudo-random number, aka nonce. This number, when combined with the data provided in the block and passed through a hash function, must produce a result that matches given conditions. For example, a hash starting with 4 zeros. When a matching result is found, the other nodes will verify the validity of the outcome, and the miner node is rewarded with a block reward. Therefore, it is impossible to add a new block into the main chain without first finding a valid nonce, which in turn generates the solution of a specific block, called block hash. Each validated block contains a block hash that represents the work done by the miner. This is why it's called proof of work. Proof of work helps to protect the network against numerous different attacks. A successful attack would require a lot of computational power and a lot of time to do the calculations, and therefore it would be inefficient since the incurred cost will be greater than the potential rewards for attacking the network. One issue with proof of work is that mining requires expensive computer hardware that consumes a large amount of power, and while complicated algorithm calculations guarantee the security of the network, these calculations aren't able to be utilized beyond that. While proof of work may not be the most efficient solution, it is still one of the most popular methods of reaching consensus in blockchains. There are already alternative methods and approaches trying to solve the problem, but only time will tell what method will be the successor of proof of work. Stay tuned for more content, and don't forget to check out our other videos at Binance Academy.
Mining. Last edit at Corwin Times, January 12, 2023. Proof of work is no longer underlying Ethereum's consensus mechanism, meaning mining has been switched off. Instead, Ethereum is secured. Prerequisites. What is Ethereum mining? Mining is the process of creating a block of transactions to be added to the Ethereum blockchain in Ethereum's now deprecated proof of work architecture. The word mining originates in the context of how Ethereum transactions were mined. The following provides an overview of how transactions were mined in Ethereum proof of work. An analogous description of this process for Ethereum proof of stake can be found here. A user writes and signs a transaction request with the private key of some account. The user broadcasts the transaction request to the entire Ethereum network from some node. Upon hearing about the new transaction request, each node in the Ethereum network adds the request to their local mempool, a list of all transaction requests they've heard about that have not yet been committed to the blockchain in a block. Block. Transaction fees. Verifies the validity of each transaction request, i.e. Verifies the validity of each transaction request, i.e. no one is trying to transfer Ether out of an account they haven't produced a signature for, the request is not malformed, etc. And then executes the code of the request, altering the state of their local copy of the EVM. The miner awards the transaction fee for each such transaction request to their own account. Begins the process of producing the proof of work, certificate of legitimacy, for the potential block, once all transaction requests in the block have been verified and executed on the local EVM copy. Eventually, a miner will finish producing a certificate for a block which includes our specific transaction request. The miner then broadcasts the completed block, which includes the certificate in a checksum of the claimed new EVM state. Other nodes here about the new block. They verify the certificate, execute all transactions on the block themselves, including the transaction originally broadcasted by our user, and verify that the checksum of their new EVM state after the execution of all transactions matches the checksum of the state claimed by the miner's block. Only then do these nodes append this block to the tail of their blockchain, and accept the new EVM state as the canonical state. Each node removes all transactions in the new block from their local mempool of unfulfilled transaction requests. New nodes joining the network download all blocks in sequence, including the block containing our transaction of interest. They initialize a local EVM copy, which starts as a blank state EVM, and begins the process of producing, verifies the validity of each transaction request, i.e. no one is trying to transfer Ether out of an account they haven't produced a signature for, the request is not malformed, etc. And then executes the code of the request, altering the state of their local copy of the EVM. The miner awards the transaction fee for each such transaction request to their own account. Begins the process of producing the proof of work, certificate of legitimacy, for the potential block, once all transaction requests in the block have been verified and executed on the local EVM copy. Eventually, a miner will finish producing a certificate for a block which includes our specific transaction request. The miner then broadcasts the completed block, which includes the certificate in a checksum of the claimed new EVM state. Other nodes. Other nodes here about the new block. They verify the certificate, execute all transactions on the block themselves, including the transaction originally broadcasted by our user, and verify that the checksum of their new EVM state after the execution of all transactions matches the checksum of the state claimed by the miner's block. Only then do these nodes append this block to the tail of their blockchain, and accept the new EVM state as the canonical state. Each node removes all transactions in the new block from their local mempool of unfulfilled transaction requests. New nodes joining the network download all blocks in sequence, including the block containing our transaction of interest. They initialize a local EVM copy, which starts as a blank state EVM, and then go through the process of executing every transaction in every block on top of their local EVM copy, verifying state checksums at each block along the way. Every transaction is mined, included in a new block and propagated for the first time, once, but executed and verified by every participant in the process of advancing the canonical EVM state. This highlights one of the central mantras of blockchain: don't trust, verify. A visual demo. Mining algorithms. Last edit at Rex 40. Dagger Hashimoto. Dagger Hashimoto was a precursor research algorithm for Ethereum mining that Ethish superseded. It was an amalgamation of two different algorithms, Dagger and Hashimoto. It was only ever a research implementation and was superseded by Ethish by the time Ethereum mainnet launched. Dagger involves the generation of a directed acyclic graph, random slices of which get hashed together. The core principle is that each nonce only requires a small portion of a large
So I understand it, but it's still not clear how, because from reading this documentation is not clear whether or not, because it says at some point that nodes propagate the transactions over the network, but at the same time it says that they propagate the blocks. So it's not clear what's the line there, if there is any line. What is the mechanism that determines if they are going to propagate blocks or if they're going to propagate transactions for other nodes to validate? It doesn't make sense. So I think the only way is probably to study the source code to understand. Unless I'm missing something, but I think I read this like 3 times already and still don't understand.
The core principle is that each nonce only requires a small portion of a large total data tree. Recomputing the subtree for each nonce is prohibitive for mining, hence the need to store the tree, but okay for a single nonce's worth of verification. Dagger was designed to be an alternative to existing algorithms like SCRYPT, which are memory hard but difficult to verify when their memory hardness increases to genuinely secure levels. However, Dagger was vulnerable to shared memory hardware acceleration and dropped in favor of other avenues of research. Hashimoto is an algorithm that adds ASIC resistance by being I/O bound, i.e. memory reads are the limiting factor in the mining process. The theory is that RAM is more available than computation. Billions of dollars worth of research have already investigated optimizing RAM for different use cases, which often involve near random access patterns, hence, random access memory. As a result, existing RAM is likely to be moderately close to optimal for evaluating the algorithm. Hashimoto uses the blockchain as a source of data, simultaneously satisfying 1 and 3 above. Dagger Hashimoto used amended versions of the Dagger and Hashimoto algorithms. The difference between Dagger Hashimoto and Hashimoto is that, instead of using the blockchain as a data source, Dagger Hashimoto uses a custom-generated dataset, which updates based on block data every n blocks. The dataset is generated using the Dagger algorithm, allowing for efficiently calculating a subset specific to every nonce for the light client verification algorithm. The difference between Dagger Hashimoto and Dagger is that, unlike in the original Dagger, the dataset used to query the block is semi-permanent, only being updated at occasional intervals, e.g. once per week. This means that the portion of the effort of generating the dataset is close to zero, so Sergio Lerner's arguments regarding shared memory speedups become negligible. More on Dagger Hashimoto. Ethish. Ethish was the mining algorithm that was actually used on the real Ethereum mainnet under the now deprecated proof-of-work architecture. Ethish was effectively a new name given to a specific version of Dagger Hashimoto after the algorithm got significantly updated, whilst still inheriting the fundamental principles of its predecessor. Ethereum mainnet only ever used Ethish. Dagger Hashimoto was an R&D version of the mining algorithm that was superseded before mining started on Ethereum mainnet. More on Ethish. Further reading.
Oh, maybe if I ask ChatGPT. But I know that he's not. I think he's not gonna give me a good answer. It determines when. Yeah, so I think it is the way that I'm thinking about it is correct. It's just that it is too difficult to gain more velocity than the entire network, which is the whole 51% attack. But then it is unstable because of MEV it centralizes too much. Because of the velocity of the transactions and the whole thing about building them off-chain. But this is where it gets confusing. So maybe I don't understand it really well yet. Yeah, but that's what I'm saying. Maybe ChatGPT is wrong. The way that I'm thinking about it is if a portion of the network receives a lot more transactions than another portion, because obviously they are passing transactions around, but if one of the portions of the network receives like batches a bunch of transactions off chain, in order to increase MEV, and then they put those transactions on chain, there is going to be an imbalance of the flow of information inside of the network. So those nodes that are directly connected to the flow that is bigger, it's kind of like a river, if you think about it. So the ones that are connected to the ones that have the highest flow of information are going to pass more blocks. So it means that their local history is going to be different than other nodes' local history. And in my mind, this is the same as the... but maybe it's not, because you're going to have two different histories at the same time. Like, the delay of the information across the network is going to determine the rate of uncle blocks, because each node is going to have a discrepancy on its history that is equivalent to the difference in the flow of the network from each node. So in my mind, it makes sense that the rate of uncle blocks is directly connected to the flow of information on each node, because the discrepancies of the network is what creates the uncle blocks. And the whole problem of MEV is the synchronization of these differences in flow from each node. Mining and block out. But the thing that I don't understand is this stuff. That it says that uncle blocks is when they both mine and block at the same time. Like, that's the thing that might be wrong in my mind. So I guess like this is because it's gonna talk about the whole proof of work thing. And blah blah blah. And this doesn't answer the question. That's the thing. Let's say they have different histories, then how, at some point, it's gonna be by the block difficulty, because the lowest one wins. But how the importance is the timing, I think. Yeah, it's all about the timing. Because I think that each node compares itself. I remember asking that as well. So each node compares itself with its neighbors from time to time, the history. And then based on that, they converge, I think. So how can I ask this? Because if one node is mining, is the thing that I'm thinking about, the scenario that I'm picturing in my mind is if you have one node that only propagates blocks through the network. But I guess like that's the thing that is difficult to understand because it will have to receive other transactions as well. That's the thing. Yeah, I'm thinking about a node that receives all transactions off the chain and then builds the blocks and then propagates the blocks. And then on top of that, it mines the transactions that it receives from its peers as well. So let's say it's just a lot faster. Like it does a bunch of transactions off the chain and then also computes the transactions that is receiving from its nodes. Like what happens then? But the issue is that it's just this it's a matter of these nuances of the size, like the computational power, the size of each block, and the flow of information for each block, for each node. Ethereum, the order of blocks being propagated by different nodes does not necessarily determine which block is added to the chain. Mine blocks simultaneously and propagate them to the network. Occurs with some nodes following one chain and others following another. Yeah, that's what I'm talking about. So this is what I'm saying. Like, it is directly correlated. Because if one of the nodes has a lot more information than other nodes, then it's going to create more uncle blocks in the chain because of the friction that it creates. It's like a waterfall, let's say, or a bunch of water flowing from one node, and then as it goes through the other ones, that there is a delay. So it always creates the bunch, like the higher the flow, the higher the difference in flow, the greater the uncle rate, I think. But ChatGPT is saying that it is not, so this is why I'm confused. So maybe it's just a thing about semantics, that I'm thinking about a fork, but I'm thinking about a fork, but I'm saying uncle. So, and what I mean by uncle, it's ChatGPT understands that it's a fork instead. Continue to build on the chain that they first received. So some nodes may continue building on the block created by node X, may continue by block Z. This creates two different chains that contain different transactions and have different block heights. The consensus mechanism of Ethereum ensures that the network eventually converges to a single chain by choosing the longest valid chain. Miners in the network will continue to add new blocks to the chain that they are building on, and the chain with the most blocks will eventually become the longest chain, considering the valid chain. Therefore, in the scenario described, the block that is added to the chain depends on which block is mined next. Chain the majority of miners build on. The order of blocks being propagated to nodes does not necessarily determine which transactions. So is the flow. Let's say one of the nodes receives a bunch of transactions. Transactions that were validated off-chain and propagates them as blocks to the chain. Does the flow of transactions, difference in flow of transactions from different nodes directly or related with the amounts of forks network. Difference in flow of transactions from different nodes is one factor that can lead to forks in the Ethereum network. When nodes receive different sets of transactions and attempt to create blocks from them, it is possible for multiple blocks to be created simultaneously. This can result in temporary forks in the blockchain, so that's the whole thing. I think I got it. That's why they changed for proof of stake to separate into two, and also because it's the solution that they found to this problem. And to create the time. So if you make it based on the timing, then it changes this whole thing. So now I have to understand how it works on proof of stake. Because now the question is on proof of stake, because the one thing that I didn't understand in proof of stake is that it says it is by the timing, but what happens, because at different moments in the network you're gonna have more or less blocks being created depending on how many transactions are being propagated, obviously. So in higher congestion times you're gonna have more blocks, which means that, but the time frame is fixed. So I don't understand how he handles this thing. I guess the way that it's gonna handle is based on the committees, but it says that each validator has to vote based on the committee or the time, which is the epoch. So I don't really understand the correlation between the number of blocks and the voting system on the proof of stake. That's what I need to understand. But I think I'm not gonna dive into the algorithm. I think maybe in the future, but I think it's a bigger ROI now to a bigger return on investment in my time to study the proof of stake, because it's the one being used right now, and other chains also use proof of stake as well. It's possible for multiple blocks to be created simultaneously. This can result in temporary forks in the blockchain, where different parts of the network follow different chains. The consensus mechanism, it's pretty crazy. It's like it feels like talking like with a human. Pretty insane. This can result in temporary forks. However, as I mentioned earlier, the consensus mechanism of Ethereum ensures that the network eventually converges into a single chain by choosing the longest valid chain. Therefore, temporary forks are resolved as miners add new blocks to the longest chain. The network eventually agrees on a single version of the blockchain. It is worth noting that the difference in flow of transactions is not the only factor that can lead to forks in the Ethereum network. Other factors that can contribute to the forks include hardware or software issues, network latency. So, like, I think that this wasn't, like, the biggest reason why this is centralizing is not necessarily because it's gonna allow the people that are doing the MEV thing with private relayers to change the network, because you would need you would need too much computation. So it would be like the 51% attack. So I don't think that the problem wasn't that. The problem is that it forces people to use the RPCs that have the connection to nodes that allow them to create blocks by themselves. That's the thing. To validate the block outside of the chain. Because that way you don't run the risk of front running, but then you depend on the trust assumption that the block builders that you're using through the relayer are trustworthy, because then the miners can front run you if they want, or steal your MEV. That's the thing. And if you send through any other node which is public, and it's not gonna have disadvantages, because you're gonna have to send your transaction first, because the node is not gonna have any special mechanism to build the blocks before it propagates the transaction through the network. So it means that the chances of you getting front run are a lot higher. As everyone's gonna see your transaction, and it's not gonna be. And the main fundamental difference here is the capability of the node to build a full block and propagate the full block. So this is the stuff that is unclear to me, because it seems to me that another solution would be to just force everyone to propagate transactions instead of blocks. And then, but that's the thing that is kind of still confusing, because then how does the mining algorithm works? Because if that was the case, then maybe you would be less efficient, but then you solve this problem where, like, but you don't solve the problem because obviously you're gonna have MEV still. But then at least it becomes an equal playing field, let's say, because then there's no way to validate transactions outside. So if you force everyone to send, yeah, but then how would you build the blocks? That's the thing. Because at some point the node has to build, and I think that's probably the reason. The reason why it's like this is because you can't force the node to only mine the transactions after it receives. Like it has to mine by itself in order to include the transactions, and each node has to have the capability of mining the transactions. So it becomes impossible to force each node to allow other nodes to see the transactions before. That's the reason. And the reason for having blocks is because then you can create the chain on the Merkle-Patricia tree, I think, of hashes. So you can batch a bunch of transactions, it becomes more efficient. And then the size is determined by the gas, which is the gas limits, which can vary depending on the congestion. So I think I understand everything now. So now I'm going to study the algorithms. I'm going to finish reading this stuff here again, and then I'm going to read the documentation and study this data availability sampling. I'm going to read all of this stuff. Maybe I think I'm going to stop here actually, then I'm going to go work out, and then I might come back later, or I might read some of this stuff off stream and then come back tomorrow. After I understand the algorithm for proof of stake, then I think I'll go back to studying the source code. And I'm probably gonna have to download the Lighthouse source code to study that as well. And also another thing that I realized is that the reason why I thought it only talked about 2 clients in the Ethereum documentation is because I'm not running the validator parts. So the way that it works is that the execution client executes the transactions and sends to the consensus client, and the consensus is the proof of. Yeah, that's the thing I don't understand really well, but I think that the validator client is the one that you deposit the ETH. So only if you're running the validator client, you can validate the blocks. So in order to participate in the committee, and that's where that client goes into play, but I'm not running that client here. So I think that client is only necessary if you're gonna be part of the voting, so gain rewards. And then the other ones are responsible for execution and consensus. Which the consensus, which is the Lighthouse that I'm running here, is probably the one that has this fork algorithm, the Gasper and the fork, and the other, I think is Ghost, something like that. Yeah, I have the documentation here that I'm gonna. Yeah, Casper and Casper Ghost, something like that. Ghost and Casper, this one. So I think that Lighthouse has these 2 algorithms here, and the other client is just like the block building part of validating the transactions and building blocks. I think I'm gonna stop here then. I'll probably come back tomorrow and maybe today, depending on how long it takes to work out. I might read some of this stuff off stream as well. Maybe I'll play poker as well, don't know. So probably come back tomorrow.